continuing to work on problems related to IoT security. Last year, we held this workshop at CCS in Texas, and so there we dealt with a lot more security folks. This year, we're hosting it with SIGCOMM, and we're hoping that next year it will bounce back to a security conference, potentially going back to CCS. And in terms of some interesting statistics, we had a large number of abstracts submitted. Only a small number of those ended up being converted into submissions. So we had about 28 abstracts. 19 of those became submissions. And some of the more interesting things are last year, if you look at the program, we had 6 measurement papers. So last year, a lot of the papers were about what is wrong with IoT devices? Can we actually take some packet traces and try to figure out something interesting and figure out some privacy or security violations? And this year, we've kind of gone from just a lot of these measurements to actually coming up with systems that will use the measurements to defend. And we actually have one interesting measurement paper that actually goes beyond the measurements we saw last year to trying to look into NAT and characterizations within the home. So that's going to be an interesting paper that comes up later on in the day. And as I said, we have about 32 registrant attendees, and as the day goes on, this will fill up the room. In terms of a program, we have 4 exciting sessions and 2 very interesting keynotes. So last year, the keynote focused more on actual the academic side of the defense against IoT attacks. This year, we're going to go with a more industry focus. We're going to have 2 people, one Bruce Maggs from Duke Akamai, another Haopeng Zhao from Facebook, and we'll basically get to see measurements at CDN scale and some counter defenses. And then we'll get to see edge-based security using eBPF. So you kind of get to see both what are types of attacks people are saying, and then what are the different types of mechanisms people are using to essentially defend against these attacks. And as I said, we have 4 sessions, and essentially the sessions are going to spread out throughout the day. There are 2 key changes to the program. In the first session, basically, we're going to reorder the papers just to give you a better context. So we've spoken, actually the authors reached out to us and they said reordering the papers for the first session will actually help the audience get a better idea of the context and the background before jumping into some of the very interesting nuts and bolts of the different solutions in this space. So we're going to reorder the first session, and we're actually going to move up one of the talks just because we had some scheduling issues with one of the invited talks. So we've had kind of, basically we lost one of the invited talks due to a bunch of different things, and we've been trying to figure out a way to kind of get the schedule all fixed out. And one of the things we're going to do is essentially we're going to move up one of the talks so the day will end earlier, 20 minutes earlier, 30 minutes earlier, and this will all give us a chance to go out and enjoy potentially some fireworks. And I want to essentially thank the program committee, because without them, nothing would actually have gotten done. They did extensive work selecting papers, and I also want to thank all of the authors that submitted papers, just because without them, there would be no conference. And I want to thank all of you for actually coming in here and waking up early to come in here. So with that, I'm going to hand it over to the first session chair, Gianni, and then we'll essentially go through into session 1 and talk about I guess I'll just let him come up. But we'll talk about some MOD-based policies for IoT security.
Good morning, everyone. So let me introduce you the first session, which is verification with MODs. And the first speaker is going to be Dinesha Ranathunga, and is going to present paper Clear as MOD, generating, validating, and applying IoT behavioral profiles. And Dinesha is a postdoctoral researcher at the School of Mathematical Sciences at the University of Adelaide, Australia. His main research interests are in provable network security in domains such as critical infrastructure, SDN, and IoT. So welcome the first speaker.
Thanks, Gianni. Good morning, everyone. Today, I'm going to be talking a little bit about some work that we've done recently in the space of IoT security. We did this work jointly with our research partners at UNSW. So we know that IoT devices are increasingly coming under cyber attack. Last year, for example, there was a malware called Brickabot, which attacked and damaged over 10 million IoT devices. Brickabot. Can you hear me now? Perfect. So Brickabot scanned the internet for vulnerable IoT devices, and when it found one, it corrupted the device's flash memory with random data, and that made the device inoperable. So to recover it, you had to reinstall its firmware, and in most cases, the damage was permanent. You had to actually replace the entire device. So Brickabot affected hundreds of thousands of modems and routers belonging to internet service providers and telecom service providers. And as a result, their users couldn't access the internet and other network resources for longer periods of time. Likewise, the year before, there was a large-scale IoT botnet called Mirai, which was used by hackers. Mirai comprised of tens of millions of compromised consumer IoT devices like IP cameras. Using Mirai, hackers launched a DDoS attack on a large-scale DNS provider called DIN. As a result, DIN went offline, and lots of internet service platforms like Amazon, PayPal, and Twitter, which relied on DIN to function, also suffered service outages. It's estimated that the revenue lost by these companies because of the Mirai attack is in the order of hundreds of millions of dollars. So this cybersecurity risk that IoT devices pose both to corporations and people, it's only going to get worse with time. Currently, we have over 20 billion IoT devices in operation. It's estimated that figure will exceed 70 billion by 2025. With the push to launch new technologies like driverless cars and large-scale drone-based military operations in the future, this problem is going to grow in orders of magnitude unless we take some significant steps now. So what are some of the key drivers behind these IoT-based attacks? Well, for one, IoT devices often have highly limited CPU power. If you take a smart bulb, for example, it comes with a low-performing CPU, and that's because it's designed to consume minimal power. So you can't run sophisticated applications like an antivirus program on a smart bulb. It's not a practical way to detect and mitigate malware attacks. Also, when it comes to patching security vulnerabilities, that can be quite challenging with IoT devices. But most importantly, the lack of formal specifications by IoT vendors on the intended behavior of their devices is actually promoting these IoT-based attacks. After all, a manufacturer has the best knowledge of what network services are required by their devices to function. Without their clear specification, an operator just can't lock down the device behavior in a network and also easily detect anomalous behavior, which could indicate that the device has been compromised. So our research particularly focuses on that problem. We look at ways to lock down IoT device behavior in a network and how that behavior can be checked rigorously. So the IETF is actually pushing vendors to provide formal specifications for their intended device behavior in the form of a MUD profile, which stands for Manufacturer Usage Description. Basically, what a MUD profile is it captures a set of rules which describe traffic flows allowed in and out of an IoT device. MUD is lightweight. It relies on the fact that IoT devices often have a small and recognizable communication pattern. And it's also aimed to be high level because a MUD profile describes behavior. It's meant to only change when the behavior changes, not when the operational environment changes. So this decoupling between behavior and the underlying network implementation is achieved in MUD via abstractions. So the MUD specification provides abstractions, for example, to allow the device to communicate with the local controller, the local gateway, devices belonging to the same manufacturer, and so on. So the idea is when one of these MUD profiles gets implemented in the network, those abstractions will be refined to suit the local implementation. Using a MUD profile, a network can automatically configure the network services required by an IoT device to function properly. It also allows a network operator to easily detect anomalous device behavior, which could indicate that the device has been compromised. So essentially, MUD is a very effective way of enforcing baseline security in a network. Here we have an example MUD profile. This is for a blip care blood pressure monitor, which we had up and running in our testbed. The actual MUD profile had several hundred lines of code. I've just taken a partial snippet. I just want to highlight a few key points. As I said before, MUD profile captures a set of rules which describe the intended traffic flows in and out of an IoT device. So this particular snippet shows one such rule. This rule allows DNS traffic into the IoT device from its controller. The way we've described this is using the protocol, IP protocol number, the source port number in this case, and also the endpoint initiating the traffic flow. We've used the MUD abstraction controller to indicate that it's the controller who's initiating the traffic. So the thing to note here is that the syntax and the semantics of this description must strictly adhere to the IETF MUD specification, otherwise the MUD profile is not valid. And given that you can have several hundred lines of code, at least in a MUD profile, this is not something trivial that you can do by hand. You actually need automated tools to do this efficiently and accurately. So the MUD profile, however, is still in a draft stage. So vendors don't have, they have not provided actual MUD profiles for their devices, and they also don't have tools freely available that allows them to easily generate these MUD profiles. So that's where our research comes in. We've generated two tools, Mudgy and Muddy. Mudgy allows an IoT vendor to easily generate a MUD profile for their device using the device's traffic trace. And Muddy allows to check the correctness of that MUD profile and also check compliance against an organizational security policy. Why do we care about such compliance checks? Well, in certain domains like SCADA networks, which drive the critical infrastructures like power and water plants, you need absolute assurance before you deploy an IoT device into the network that it's not going to open up your power plant to cyber attacks. Particularly in SCADA networks, they employ highly restrictive cybersecurity practices, and this is to prevent serious injury to people and even death. So using these compliance checks in Muddy, we can ask questions like, can I safely deploy this IoT device in my power plant? So we know that IoT devices can communicate online as well as on the local network. If you take a consumer IoT device like an IP camera, it uses remote services provided by cloud servers and also exposes services locally, for example, to a user's mobile application. Mudgy can track these traffic flows in and out of an IoT device and generate its traffic trace. Here we have an example traffic trace that we've generated for the blip care blood pressure monitor. As you can see, the behavior of this device can be captured by a few tightly defined traffic flow rules. What I mean by tightly defined is the traffic flow rules have a narrow IP address range and also a port number range. So if you look at the first two rules, for example, it allows the device to communicate with its controller, which is given by this IP address, for DNS requests and responses. And the last two rules allow it to communicate with its online server at this domain name, and this is to upload the blood pressure measurements to the online server. So you can, this device has purely static functionality. You can lock down its behavior using a few tightly defined traffic flow rules. In fact, majority of the testbed devices that we had up and running in our network conform to this category. Once we generated the traffic trace, we could use Mudgy to convert that into a MUD profile. When we generate a MUD profile, we use an application whitelisting policy. That means you have multiple allow rules in your MUD profile with a single drop all rule. We could use multiple drop rules, but that would give rise to ambiguities, which you can only resolve if you have a notion of rule priority. And the current IETF MUD specification doesn't support a notion of rule priority, and that is to keep the complexity of the MUD profiles low. So we keep with the theme, and we use the application whitelisting model to achieve these targets. So here we have a summary of the testbed devices we had running. As you can see, we had several IP cameras, some air quality monitors, some medical devices like the blip care blood pressure monitor, several switches, some smart bulbs, multimedia devices, and so on. So we generated the traffic traces for each of these using Mudgy, and then we inspected their behaviors to categorize them into groups. We found that we could class them into three categories. So marked in green are your devices which have purely static functionality. So like the blip care blood pressure monitor, you can lock down these devices' behaviors using tightly defined traffic flow rules. What that means is in the network, you can enforce a very tight security baseline for these types of devices and reduce the attack surface of the network quite significantly. The second group, that's marked in blue. So these devices also had static functionality, but you could only define that quite loosely. You'll notice that there are several IP cameras in this group. So these IP cameras used a protocol called STUN, which stands for Session Traversal Utilities for NAT. A camera uses this protocol to verify that its mobile user's application, for example, can stream video directly from the camera over the internet. And when a camera uses this protocol, it usually communicates with its stun servers on a broad range of IP addresses and port numbers. And because of this communication, we can't describe the behavior using narrow traffic flow rules. We can only define it quite broadly. So what that means is in the MUD profile, you'll have MUD rules which are quite broad, and as a result, the baseline security you can enforce for these types of devices is quite not as tight as in the previous case. So the third group is marked in red. So these are devices which had complex and dynamic behavior. An example is the Amazon Echo speaker. It can communicate with a growing number of endpoints. You can't anticipate those endpoints in advance. For example, with the Amazon Echo, you can ask it to switch a smart bulb in your network on and off, and you can also ask it to stream news from an online website. So you cannot anticipate those endpoints in advance. The challenge for manufacturers with these devices is how they can dynamically update the MUD profiles to reflect the capabilities that are enabled in an IoT device at a given point of time. So once we generated the MUD profiles, we started checking them. We used MUDI to check for inconsistencies like conflicts and redundancies. Because we use an application whitelisting model, we remove conflicts by design, but we still have redundancies are still possible, so we check for these using MUDI. Apart from correctness, we also check these MUD profiles for compliance with an organizational security policy. As I said before, these types of compliance checks are critical in SCADA networks. We've developed an organizational security policy using SCADA best practice guidelines, and that is because SCADA best practices offer a wide spectrum of security policies which cater for various organizations. For example, they provide security policies for the highly restrictive SCADA zone, which, for example, can run a power plant, and also policies for the more moderately restrictive environments like your corporate networks and your demilitarized zones and so on. We also developed a formal framework to compare these MUD policies against the organizational security policy. I'm not going to go into the details of the formal algebras. You can find them in our publication here. But at a high level, what it does is basically it generates canonical forms of the MUD policy and also the organizational security policy. And then it derives partitions of those canonical policies based on the semantics, and then does an inclusion check to see if the MUD policy is included in the organizational security policy. So using these formal framework, we can check, for example, if a MUD policy, if a device can be safely deployed in a power plant. By safely, what we mean is without breaching organizational security policy. So MUDI also represents MUD policies using formal constructs underneath. By using formal constructs, we capture policy properties explicitly and we remove any implicit properties. But most importantly, we can formally reason about policy. So we can ask questions like, is my MUD policy consistent? A thing to keep in mind when using formal constructs to represent MUD policies is that MUD policies are meant to be high level, independent of any underlying network implementation details. So the formal constructs that we choose should have high level expressiveness. So mathematical abstraction that meets these requirements is a metagraph. A metagraph supports high level expressiveness, but most importantly, it provides strong mathematical underpinnings, which you can use to capture policy properties explicitly, and also check underlying properties like consistency accurately. So what is a metagraph? Well, simply put, a metagraph is a directed graph between a collection of sets. Each set is a node in the metagraph, and each directed edge represents a relationship between two nodes. Here we have an example metagraph of a LifeX bulbs MUD policy. As you can see, the nodes in this case consist of the device and also the network resources the device is allowed to access. Each of these directed edges describe how the device is allowed to access those network resources. For example, it can access the local gateway for DNS queries and responses. It can also access this public time server pool.ntp for time synchronization using NTP. You'll notice that there are attributes associated with these edges. So metagraphs can support attributes on the edges. A particular type of metagraph that supports propositions as attributes is a conditional metagraph. And we find that conditional metagraphs are very useful in modeling policies that are activated conditionally. So in this case, for example, with a MUD policy, device can access the local gateway when the traffic matches certain IP protocol numbers and port numbers. So we can capture those as propositions on the edge. And MUDI uses a conditional metagraph underneath to model these policies. So once we developed these MUD policy metagraph models, we looked at ways of concretely instantiating them. So we could check important properties like consistency. We looked for an off-the-shelf tool we could use to do this with, but unfortunately we couldn't find any, so we ended up writing our own. It's called MG Toolkit. It's an open source Python package. You can download it from PyPy on this link. Basically, it allows a user to instantiate a metagraph, apply metagraph operations, and check results. It's also an object-oriented API, so it comes with several classes. For example, a conditional metagraph class, which MUDI uses underneath to instantiate the MUD policies. This class also has several members, which it uses, for example, to check consistency and so on. So here we have a summary of our results. As you can see, we found redundancies for some of the MUD policies. For example, the Belkin camera had 3 redundancies. These stemmed from overlapping traffic flows in the MUD profile, which enabled ICMP into the device. These redundancies indicate that there is some level of inefficiency in the MUD profile. And the reason why we track these redundancies is because we are automatically generating the MUD profiles. So if we are getting a high count of redundancies, that indicate that there's something that we need to improve in the algorithms. When we check the MUD policies for compliance, for example, with the BlipCap blood pressure monitor, we found that we could install that in the demilitarized zone or the enterprise zone, but not in the SCADA zone. 50% of the SCADA, MUD rules violated the SCADA zone policy. On the other hand, the Belkin camera, we found that we could only install that in the demilitarized zone. 52% of its rules violated the SCADA zone policy, and 11% violated the enterprise zone policy. So the great thing with MUD is that not only does it tell you whether your MUD policy is compliant with the organizational policy, it also gives you an idea of which MUD rules are actually triggering these violations. So you can find potential workarounds. For example, with the Belkin camera, if you localize all your DNS communications using local DNS servers, you're one step closer to achieving compliance in the SCADA zone. So to wrap things up, the lack of formal specifications by IoT vendors on the intended behavior of their IoT devices is actually promoting cyber attacks using IoT devices. The IETF is trying to combat this problem via the MUD proposal. MUD allows to lock down the IoT device behavior in a network and also enforce quite a strict security baseline for them. We've developed some tools that help with this cause. MUDI allows an IoT vendor to easily generate a MUD profile for their device, and MUDI allows to check the correctness of that device and also compliance using a formal framework. So I'm going to stop there, but the next paper that follows with Ayyoob, he'll talk more about how we use MUD for verification at runtime. This was basically how we used that prior to deployment. Thank you.
Any questions?
In terms of the actual percentages? Yeah, so when you compare that with the actual MUD rules, I think it was less than 25%. Yeah. Yes. Yeah, absolutely. What we're trying to do is have a systematic way of reducing the attack surface in a network. So if, for example, if you're plugging in an IoT device in a network and it's only allowing the bare minimum services that it requires to function, that is a starting point. But from there on, as you say, other vulnerabilities, things like that, potentially could be included in the actual MUD profile down the track. So things like, CV information to automatically detect, how vulnerable the device is in a network. So these are things that we are looking down the track as well.
So then if I may follow up, so then how is this different from firewall rules?
Well, I suppose what we're trying to do is basically configure firewall rules based on the device's behavior. Yes.
Any other question? I have actually.
Yes.
I wonder, like, you analyze like a different device. Did you find one of them that has like a kind of weird behavior or something like that you didn't expect, only was behaving like a kind of in terms of, let's say, traffic in a way that it was unexpected? Or
Yeah, that's a good question. Well, the thing is, we had these devices running in our test bed, and these are used by different people for different purposes. So one of the first things that came into mind was, is this genuine traffic or is it attack traffic that people just use for tests? So Ayyoob actually did the work on this, developing Maji. So what he did was basically do volumetric analysis on the actual hits we were getting and separated the general behavior from the actual random ones. Yeah.
any other question?
Because it's still in draft stage, I'm not sure exactly what percentage, but not many. Absolutely. So, I mean, not every type of attack can be prevented through mud, but I think this is basically, you're doing things proactively to reduce the attack surface in your network, and then add additional mitigation mechanisms on top to deal with scenarios like that. Yeah.
Any other question? Okay, let me introduce the second paper of the session. The second paper is combining MUD policies with SDN for IoT intrusion detection. And the presenter is Ayyoob Hamza, which is currently a PhD student, a PhD candidate at the University of New South Wales in Australia. Prior to his research career, he worked in the industry for 3 years, working on IoT solution development, in IoT solutions development. His research interests include Internet of Things, network security, distributed systems, and software-defined networking.
Thank you, Jen. Hi, everyone. I'm Ayyoob, and this is our paper combining MUD policies with SDN for IoT intrusion detection. So in the previous paper, Dinesha basically explained about the static analysis of MUD, how MUD can be generated, whether can we generate the MUD profile in a tightly manner. In here, we are trying to analyze on the deployment phase. So once we translated this MUD profile into access control, even if the rules are tight enough, does it secure the devices? So basically, that's the main idea of this paper. So when we look at, in brief, we knew that IoT devices are vulnerable. It's used to attack popular servers, and also these devices does not have any host site protection. Because of this nature, these devices are even vulnerable to simplest kind of attacks. So basically, if we look up in the existing intrusion detection solution, when we look at the hardware base, which is mostly expensive, and when you look at the software side, software solution, basically it could be either unscalable due to high rate of packets, or the other nation is because of the low accuracy. The reason of low accuracy is each of these devices are in behavior, it's very much different, and it is difficult to find the normal behavior of these devices. So in that case, it is difficult to achieve a high accuracy. So finally, this normal behavior is very much known to the manufacturer, because manufacturer is the one who implemented it, and it's the most sensible approach. So MUD proposes that idea. It says, okay, if a device has a recognizable pattern, let the manufacturer decide it, and even if there's a firmware upgrade or anything, he knows about it, and they should be able to update the profile of the device as well. So with that in mind, our contribution of this paper is threefold. So first one is focused on how we could translate these MUD profiles in an SDN environment. So while doing it, there are key factors that we have to consider. What is the scalability of using an SDN and MUD? Because in this, when you look at MUD, there's like proactive and like static and dynamic flow rules. So when we translated what are the packets, flow growth and everything going to impact, and also packet that we have to inspect. So the next one is once we translate this into flow rules, and then we analyze in around 28 IoT devices, and then based on this, we try to understand what kind of attacks still can be launched on these devices from either from the local network or towards the local network or from internet or towards the internet. So basically, after analyzing, while doing it, we thought of how we could integrate existing intrusion detection system into the architecture. For this, we used the SNOT IDS. So with that, this is a visualization of a mud profile. So basically, if you look at this, it has two separation. One is the local network and the internet communication. So in the local communication, it exposes two ports, which is 80 and 8080. Basically, it exposes a local server that can be communicated by any local IP. Here, the reason we have mentioned is any local IP is because any application can control this mobile device. So since we don't know what is the endpoint of this device, so because of this, we have to expose all the communication for that specific port in the local network. Whereas in the internet, we have mostly the dynamic access control rule, which is associated with a domain name. So in this sense, so we have both static and dynamic set of access control rules. And also, when you think about this mud profile, the device basically advertise this profile through the mud URL. So mud URL is a URL basically that can be used to identify the location of the mud profile. So with that in mind, so basically this mud URL can be exposed using DHCP or LLDP or during the authentication EAP protocol. So with that in mind, I'll explain our architecture. So basically in here, in the left side, we have the devices in the local network, which either can communicate it in the local network itself, or it can communicate to the internet over the gateway. So let me explain it through the flow execution. So initially, these devices will expose their mud URL through DHCP or LLDP or anything. So because of this, we had to capture this specific packet. So first, by default, the SDN controller through an app will be pushing a flow that will capture this DHCP packet, and then we'll be mirroring to our inspection engine. So basically, from the inspection engine, once we extract the mud URL, then we'll try to fetch the mud profile from the mud file server. So the mud files, after fetching the mud file, basically it will have two sets of access control. One is the static access control, and the other one is the dynamic access control, which is associated with a DNS name, with a domain name. So when you look at these domain names, it's associated with a DNS binding. Basically, it has IPs associated with it. So due to this nature, we have to continuously monitor the domain names that the device is sending. And while the domain name that the device is requesting, basically we have to capture those. And whenever a new communication is happening to those domain, we have to capture those certain packets, and then we have to correlate whether if there's a DNS binding associated with it, and if those access control is already defined or conforms to the mud profile. So we have to cross-check. So there are certain computation happening. So we have to continuously monitor this. So while doing this, if there is any packet that does not conform to the mud profile, will be basically mirrored to the intrusion detection system. So with that, I'll explain briefly about the flow structure. This is one of the devices that we have, which is a canary camera flow rules. So basically, when we look at the mud profile, it doesn't have a notion of priorities in it. So because of that, since we had to decide on which order these access control has to translate into flow rules. So because of that, we have three categories. One is the first one with the highest priority, which is the device to gateway or broadcast or multicast communication. Basically, we have given the high priority to that. And while doing that, we basically, on the flow number 7, we basically mirror all the communication from all the communication of the DNS response will be captured, and then it will be mirrored to the inspection engine, basically to identify what are the DNS binding, and then to later identify what are the internet communication is going to be associated with that domain name. So initially, we have shown that in the yellow color that the communication that does with a domain name, even though this, when it comes to translate into flow rules, we have to map these domain name into IP addresses. So basically, in order to do that, we have flow number 20 and 21, which basically mirrors all the internet communication to the inspection engine. And while it's doing, our inspection engine will continuously monitor whether if there is a DNS domain name that has been already associated with that specific flow. If that flow has been matched, then basically we reactively push that flow. So one of the concerns that we have to think about is when we push a reactive flow, how long do we have to maintain that flow in the switch? Because this flow, the lifetime of this flow could either depend on the TTL of the DNS packet or the DNS cache available in this device. So basically, because of this, we have to decide how long these flow need to be in the switch. Because of this, we have used the idle timeout. And then later, lastly, we have the local communication. So local communication is anything that towards the device will be above the last row, which is basically anything that does not match to the device, basically mirror it. So in here, we have like two separation. For example, 20 and 21, flow number 20 and 21 matches to the flow that basically any internet communication will be mirrored. And the line number 24 is matching to any local communication. So anything that does not conform to the MUD profile basically will be mirrored to the inspection engine. So with that, lastly, I'll just give an example. So if we have a certain flow rule, let's say if there's a local server that's running on the canary camera that in the local application communicate it to. So in this case, if we give high priority to this specific flow, then the problem that it'll generate is that we could have a spoofing technique where we could spoof the source port, and then rather we could use an internet attack, attack on an internet server, basically spoofing those port numbers. So this is why when we design these flow rules, we have to think about these conflicts, and then we have to make sure that none of these attacks can sneak in through. So with that in mind, we have a test bed that we collected like 28 out of devices. With that, we collected data for 4.5 months. And in order to verify our architecture, we built an SDN native simulator. Basically, what it does is it takes this PCAP trace and inputs into our simulator. And based on, in top of our simulator, we have built our implementation. And it checks the scalability and how these MUD profile has been translated into flow rules. While doing it, what are the possible ways of sneaking in? So we have analyzed on that. And basically, when we have a set of flow rules, set of packets that still can sneak in, set of packets that can be trapped, we basically export those packets into a separate PCAP file, and then we replay those packets into a Snort IDS. So when we look at the performance metric of this SDN solution, then there are two aspects that we have to think when it comes to cost. One is the packet inspection itself, because since we are reactively pushing flow rules to the switch while inspecting DNS bindings, in that case, we have to mirror the DNS packet plus the first few packets that associated with the certain flow for the internet communication. So because of this, there's a cost that associated with the packets. And the next one is the TCAM usage that we have to consider, because when we have a flow growth, we have to think about how long we have to maintain the flow. If it's maintained for a long time, that means it's going to increase the number of flows in the switch. So in order to tune these two parameters, the ideal value is, for this, we have used the idle timeout. So basically what it will do is, when we increase the idle timeout, basically it will keep the flows for a long time. In that case, it will increase the number of flows in the switch. Whereas if you try to reduce the number of flows, then since it's going to be the same flow, some of the flow is going to be lost from the switch. But there are packets in the devices, there are packets that is continuously transmitting after like a sleep or like idle pattern, because if it's come after a sleep time, then it tries to communicate to the same endpoint that is previously communicated. And in that case, it's going to increase the number of packets. So in order to measure this, we basically gathered the number of flows per minute and the number of inspected packet counts. So with that, we started to analyze, okay, when we tune the idle timeout, how does this switch impact? What is the optimal value for the idle timeout? So in order to study this, what we did is we measured in the simulator, we measured with various timeouts. First, we started with 2 minutes, then 20 minutes, and 1 hour, and 3,600. So it's clear, it can be seen that in the pink color, that when you think about all 28 devices, roughly, when we try to increase the idle timeout, so the number of flows is going to be increased because we are keeping the flows alive for a long period. However, when you look at the packet inspection, when you consider the total fraction of packets compared to all the packets, we see that it's decreasing because the reason is that when we keep the same flow again, the chance of using it again is very high. Because of this, the number of packets usage is going down. However, when it comes to 2 minutes, when you look at the total fraction of packets, in 2 minutes, it is only 2% of traffic for all 28 devices. That means it's only analyzing a fragment of packets compared to the total traffic. And in those 2%, 1% belongs to the domain names, DNS response packets. So the minimum would be the 1%. So if we are to further optimize, if we increase the timeout to 7,200 seconds, that means we can reduce up to like 0.5% of packet inspection. So in order to identify the most optimal value for the timeout, what we have to think is that if we look at these both graphs, so if we look at the timeout either 1,200, we could notice that most of the devices after reaching 1,200, there is no significant change. However, if you look at the net atmos camera, it is very much inversely proportional, where when you try to increase the timeout, it is also increasing the number of flows, and also it is same inversely proportional in the total fraction of packets. So each of these devices has different kind of behaviors when it's been deployed. So when you try to use such solution in a network, we have to think about what are the kind of switches that we are using, what are the types of devices that we are using, because based off these devices and the switch capacity, it's going to change the idle timeout. For example, if you have a switch like NaviFlow, which could handle like millions of flows, in that case, we don't think too much worry about the flow count, but in order to scale the servers, we can have a low value for the idle timeout, large value for the idle timeout. This way we can reduce the number of packets that needs to be inspected. Whereas if you have a switch like AT switch or like a normal home routers, in that case, it has a limited TCAM capacity, so which means it can only handle low number of flow rules. So in that case, we might have to reduce the timeout, but in that case, it will increase the number of packets that needs to be inspected. However, another concern that we have to think about is that each of these behavior could behave differently. So in some sense, it is more sensible to find a more optimal value for timeout for each devices. So then what we try to analyze is, once we have this deployment, what are the security implications? Means what are the kind of attacks that can be still launched on these devices even if we have a tight set of rules? So in order to analyze this, we use 28, in the existing deployment, we analyze all the devices and all the flow rules that are associated with these devices. And based on that, we try to find, is there a way to attack these devices? So we have, based on our analysis, we have categorized into 4 levels. One is to internet communication, and then from internet communication, and from and to local communication. So we analyze all these communication and try to figure out, okay, what are the ways of we can attack these devices? So one thing to notice is that most of the MUD profile actually defines the intended behavior of the device. So anything does not match to the intended behavior will be captured by the MUD, our system architecture. But there are techniques that we can use, like such evasion technique that we can use to hide our attacks that can be still behave like an intended behavior by using spoofing kind of techniques. So with this in mind, we try to analyze, okay, what are the ways of attacking these devices? So when you think about to internet communication, there are 2 main approaches that we can use to attack. One is to make the device itself compromised, or using reflection kind of techniques, where we use, without compromising, we reflect the packets. So when it comes to compromised devices, for example, attacks such as Mirage, initially what it does is it tries to scan the network, and it tries to find if there's a device with open telnet ports, and then based on that, it tries to compromise the device. So for example, if we think about the HP printer, it has a telnet port opened, but it is not used. I mean, what we analyze is it doesn't use when we, in the usage, normal communication pattern. So those kind of port does not need to be exposed. So if we have a MUD profile that says, okay, these are the intended behavior, we can block those port numbers and stop these devices to infect these devices from Mirai and other botnet kind of attacks. And the other one is when devices get compromised, these devices are going to attack a popular service or anything that can be a domain name or anything servers. If those domain names still does not conform to the MUD profile, then still we can detect those attacks. However, one thing that we have to notice is that none of these devices uses DNSSEC. So basically, we could use DNS spoofing kind of techniques. Basically, spoof these packets, DNS response packet, and then we will able to able to attack these servers by spoofing servers. And then from here, we could see that there are 3 different colors. One is indicated in red are the devices that use a STAN protocol. Basically, when you use STAN protocol, we have to expose the whole communication to that specific protocol. In a TCP, for example, August doorbell camera has, in that case, since it's using a TCP server, we have to expose the whole TCP communication. And in that case, anything that any attacks that launch towards the TCP will not be able to detect it using the MUD. So the yellow ones are indicated are the vulnerable devices that does not support DNSSEC. So basically, we could use DNS spoofing to attack such devices. So the next one is the attacks that originated from the internet towards the devices. Basically, the reason for these such attacks is either we have no NAT or because of port forwarding. So due to this, there are different various attackers that there are. For example, Shodan is a website that basically server that tries to find all these vulnerable devices and list out it. And then the InSecCom is another popular site. Basically, it lists out all the IP cameras that is vulnerable. So the main reason of such attacks is that there is no clear policy defined of separating the local communication which does not need to be exposed outside. However, with MUD, it clearly separates the local and internet communication. And due to this, we could be able to detect such attacks. And still, if you look at the device attacks that we listed, the red ones indicates the attacks that are still vulnerable because those are still the IP cameras that we have to expose outside the whole range. In that case, if there's a local service still running on the same protocol, that means we should be able to still penetrate using spoofing technique to attack those devices. And finally is the attacks that is towards the device and from the device. So basically, if you think most of the consumer devices, it allows to communicate to applications. So since this application endpoints is like dynamics, so we cannot restrict what are the endpoints it can communicate to. But when it comes to industry device, in enterprise device, IoT devices, these devices sometimes might communicate to its own controller in the local network. So in that case, we can restrict its communication to that certain endpoint. However, in this case, since it's all wide open, and since most of the IoT devices are not authenticated and unencrypted, simply we can launch attacks. And one of the factors that we have to think about is since existing, mostly attackers try to use reconnaissance techniques, and they are mostly active, try to probe the devices to all the port numbers, like port scanning, and try to identify. But if we have MUD in place, we could detect such scanning, and we will be able to block those attacks. However, one of the aspects that we have to think is IoT devices use like local discovery protocols, like SSTP or MDNS to expose themselves. So in that case, attackers does not need to be like actively attack it. They can just passively listen to what are the devices that are out there, and based on that and the device profile, we can generate attacks simply without making any exception traffic to the device. Basically, it goes through the intended profile. So with that in mind, so next we try to understand, okay, what are the types of attacks that can be generated in the device, launched to the device. So we had a test bed that with few IoT devices, and we had attackers and the victim in the local network, and also we had the attackers and the victim in the internet. Basically, we try to understand, okay, when we launch volumetric attacks to all these combinations, whether could be still generated. So this is a data set that we gathered before this study. So basically, we wanted to check, okay, whether could we use this data and try to check whether will we be able to detect all the attacks. And interestingly, we found from those attacks, we were only able to detect 9 out of 14 attacks on Samsung camera and Netcam and Vimo stage. Basically, the reason, because we couldn't able to detect those attacks, is that all the other 5 attacks were targeted mainly through the intended flows of the device. And the next one is similar to that. We had the similar results on VMotion, where we only not able to detect up spoofing. And with that, what we did is, once we collected this exception packets, which does not go through the intended flows of the device, so we basically mirror those traffic to the snort IDS. And in the snort, from those that we detected from mud profile, from those packets, we were only able to detect only few attacks using the snort IDS, because in the snort, we used the SSTP. For example, first 2 attacks were clearly, on SSTP and SNTP, and the next one is post-scanning. So in this, it was able to detect it, but the problem is the message that the rule that captured this specific attack was not the correct one. For example, it says the suspicious inbound traffic for MSSQL port 3306. Basically, it's because these servers signatures are mostly catered to the enterprise servers or some sort, and each of these IoT devices has its own behavior, so its signatures varies from these attacks. So in that case, we need some kind of signatures that can be specifically designed for these IoT devices. So one aspect of how to handle this is that we could use the mud profile itself, because mud profile implies what is the intended behavior. Anything inverse would be a signature. So finally, we also found few interesting attacks that was only detected through the by the snort IDS, but these are the attacks that we didn't launch, but it was launched due to the port forwarding that we did. Basically, these attacks were detected, and interestingly, this provides us more information about the attacks, such as it has a blacklisted IP address and DNS amplification attacks. Such information gives us more information about the attack servers, so the network administrator can proactively able to react to these such attacks. So finally, so we were able to combine MUD and SDN and try to build this solution. And then we analyzed on 28 out of devices and tried to find what are the benefits and the limitation that of MUD profile, MUD. And then finally, we were able to integrate with the off-the-shelf ideas. And with that in mind, what we did is finally, after submission of this paper, we were able to implement this system by communicating with the SDN community and a MUD community. And based on that, we have implemented and verified this implementation as well, which we did it on the simulator. Thank you. Thank you. Any questions? So currently, we have thought about each individual switch in the network, because we wanted to monitor both local and internet traffic. So we can deploy it outside the network. Yeah, basically, in this analysis, we did both in a home context and enterprise context. Yeah, in the router. For example, in our case, what we even experimented on OpenWRT router. So basically, we have a set of routers, like home routers, which we have flashed with the OpenWRT firmware, and we have connected the SDN cable. So basically, we are trying to check, okay, how we can use it on a home network plus the enterprise network. So basically, in here, what we do is, for example, So if you look at this graph, so basically in the table, what we are trying to do is, we are trying to monitor anything that's going from the device to the gateway, and then gateway to device. So if we have these two different communications, then we could able to identify, okay, if it's going beyond the net, or if it's only in the local network itself. Yeah. No, both aspects we are focusing on deploying in the net itself. So within the net, we can monitor if it's going beyond to the gateway. If it's going beyond the net, then we can basically say, okay, if it's going beyond device MAC to gateway MAC. If it's in the local, that means it is going to be that other MACs other than the device MAC, gateway MAC, sorry. Any other questions? Yeah. No, it is something that we are pushing by ourselves. So it's something, I mean, the home router, if it supports, yeah, yeah. I mean, MUD server is simply like an HTTP server. Yeah, that is, I mean, currently the MUD draft saying, okay, every manufacturer has to have that, but we are trying to do a different approach. Okay, if we have a repository, could we advertise those profiles? Okay. So currently, we are trying to figure out, okay, there are certain vulnerabilities still there in the MUD, how we could, there are attacks that goes through the intended flows, how we could detect those and stop those. And then try to improve, I mean, there are many vulnerabilities in MUD profile. For example, in the runtime, how do we confirm if there's a firmware upgrade, if the MUD profile suddenly changes, how do we detect those, and how do we say, okay, if there's an error due to the manufacturer, the whole network is going to be compromised. How do we detect those? Okay, thank you.
All right, welcome back. We're going to have our first keynote from Professor Bruce Maggs from Duke University. I have the honor of actually introducing him. At one point in time, he was actually my mentor when I was at Duke. So I have a lot of interesting stories to tell you guys if you guys are interested after his talk. Bruce received his BS, MS, and PhD from MIT. And after that, he spent a year as a postdoc associate also at MIT. And then he worked at NEC Research Lab for a couple of years before joining Carnegie Mellon. And he's now at Duke University as a full professor. A little unknown fact, he's the Wilder chaired professor at Duke. It's actually a chair that they give people out. He's not the wildest, just the Wilder. And in his role as the VP for Research and Development at Akamai, he's done a lot of very interesting things, and his talk today will be based on some of the work he's done there, as well as some of the work he's doing outside at Duke. And Bruce needs no introduction. He's won lots of awards, including Best Data Set, Best Paper at Conext, Best Distinguished Paper at Usenet Security, IEEE Cybersecurity Innovation Award. I could keep going, but by the time I'm done, his talk will be over. So I'm going to stop and hand it over to him, and this should be a very interesting talk.
Thanks, Theo. Thanks for inviting me. It's always an honor to be invited to speak. This is going to be more of a survey talk about what Akamai is doing to protect its customers against attacks and what some of these attacks look like than it is a research talk. And I'm really going to be relying on the work done by many people at Akamai who I'm not going to be able to attribute. I think that there will be opportunity for me to answer questions during the talk if you have them. So let's keep it informal and feel free to ask. Let me give you a little bit of background about what Akamai does and what our infrastructure looks like. Boy, does this not work? Okay, so this is like a marketing department standard photo, and it scares me a little. It looks more like a thermonuclear disaster than I guess that's supposed to show us bringing light to the world or something. But so Akamai today has about 240,000 servers. They're on 1,700 different networks or ISPs around the world. They're in some 3,300 physical locations in over 130 different countries. And Akamai is in the business of helping companies who do their business on the web. So in particular, Akamai helps speed up e-commerce websites, delivers media like videos, delivers software downloads, and more has also got into the business of helping protect websites and other services from attacks online. Most of the major media companies and banks and antivirus and software companies, and especially electronic commerce companies, use Akamai to help with their business. The scale has grown quite large, so it's routine every day for Akamai's traffic to reach at least 30 terabits per second worldwide. Some days that goes over 60 terabits per second. On any given day, we see at least 600 million distinct IPv4 addresses, and today also the number of distinct IPv6 addresses seen per day is about the same as mobile carriers have switched over to using IPv6. On any given day, we serve over 3 trillion HTTP requests. That's a lot of requests. If you divide by the number of people in the world, that's hundreds per person per day. And just keeping the logs of all the requests is hundreds of terabytes per day. I want to start out by talking about distributed denial of service attacks. And these are attacks where the attacker hopes to overwhelm an online service by sending unwanted traffic. And we'll see that sometimes these attacks are launched using bot armies that may comprise many thousands of machines. And these bot armies also may be composed of compromised Internet of Things devices. And it's typically the case that an attacker looks for some way to amplify their attack, meaning that the amount of effort or the amount of network traffic that has to be expended by the attacker or by an individual device under the control of the attacker is small compared to the expense or the amount of network traffic sent in response. So this chart shows the largest attacks on a year-by-year basis seen against Akamai customers. It's an interesting chart, in part because it looks like a scary kind of exponential growth, but also because there will be dips where, for a whole year, 2017, we didn't actually see any really large-scale attack like we did in 2016 and 2018. Later in the talk, I'll detail what happened in those large attacks in 2016 and 2018. You can see that the largest attack in 2018, which peaked at 1.35 terabits per second, is large, but not really that large compared to the normal amount of traffic that Akamai serves anyway, which, as I said, is very commonly over 30 terabits per second. So a small percentage, 3 or 4% maybe, of our typical traffic. Let me tell you a little bit about the system that's used to defend against these sorts of denial of service attacks. Now, I'm going to first start out talking about a system that's not specialized to protecting websites, but can be used to protect any sort of service. It was developed by a company called Prolexic that Akamai acquired a few years ago. And the idea is that Akamai has deployed about a dozen data centers around the world that each have a lot of bandwidth. And if you have a service that's come under attack and you decide to ask Akamai to shield it or wrap it with the Prolexic system, what you do is you start to advertise an IP Anycast address as the address of your service. And so you can see here each of these different data centers represented by a server has the same network address. And so your end users will be sent automatically by the internet routing protocols to one of these data centers. And these data centers have the ability to filter out attack traffic. We'll talk a little bit about how they do that. But the hope is that they're able to tell when a legitimate user makes a request that this is not to be blocked, and then it's tunneled back to the online service that's been wrapped by Prolexic, and then the response gets tunneled back and then sent back to the user. Okay, so in a nutshell, that's how Prolexic works. It's IP Anycast. It's about a dozen locations, each of which has a lot of filtering and forwarding hardware and hopefully a lot of bandwidth. As I mentioned, in 2017, we did not have as large a peak attack, and also the number of large attacks, like over 100 gigabits per second, was down. So I'm using a slide here from 2016, which shows in the first quarter of 2016, all the attacks that were over 100 gigabits per second. So there used to be more. I don't know why. There are fewer today. I want to just pick one of these. So this was an attack that took place on March 12th, 2016. It peaked at 230 gigabits per second. And we can see that the attack was distributed among different Prolexic data centers. So IP Anycast sort of automatically load balanced the traffic amongst them. And this graph is showing that they didn't all get the same amount of traffic. So in orange, we have gigabits per second, and then in purple, megapackets per second. Okay, so this is just to give you a flavor of what Prolexic does in operation. Now, here's a trivia question for you. Akamai has a lot of customers. Which category, which industry do you think faces the most of these kind of just brute force denial of service attacks? Any ideas? Everybody gets attacked, so there's no real wrong answer, but there's one that totally dominates. Gaming industry, right? So I skipped my, that wasn't smart, I skipped ahead a slide, but yeah, so the gaming industry, these attacks are mostly aimed at the gaming industry. And the reason is that the gaming industry is very sensitive to relatively small increases in latency. So if you can you can cause 100 milliseconds latency in the response of a gaming server, the customers, the gamers, will be very upset. And the gaming industry, the game server operator will be in a difficult position, and whoever's launching the attack may be trying to shake them down and get them to pay to have the attack turned off. I share a computer room with two 17-year-old boys who are really very, very intolerant of latency. And they're always saying things to me like, "Dad, our Wi-Fi sucks." And I'm like, "Guys, do you think I don't know how to run a home network? You're not on the Wi-Fi, okay? You see that cable going into your computer? That's wired Ethernet, okay? You're plugged in directly to the home router. And we've got really almost 1 gigabit per second bidirectional fiber to the home with like 3 milliseconds first hop latency." I say this quite authoritatively. And then they say, "Fine, Dad, Akamai sucks." Yeah, it's a tough crowd. So the gaming industry is plagued by these sorts of attacks. What are these attacks? Well, there's a wide variety of different attacks that are launched. I'm not going to go through the details of each of them, but a couple of things to notice here. First of all, most of these attacks are not really application level attacks. They're not trying to bring down these services by loading up a server of some kind. They're often trying to do the attack at a lower level, maybe some kernel service. So this is just frequency of different kinds of attacks in Q4 2017. A common thing is to send packets that are slightly malformed or fragmented, or just something that will cause the recipient to do extra work. And as I said before, there's often an attempt by the attacker to leverage some sort of amplification. And there are well-known analyses of how much amplification different kinds of attacks might yield. And I'm going to show you this graph that you can go download yourself, the latest update for different types of services and how vulnerable they are to amplification, because there's some asymmetry in the amount of work that the sender may have to do in response to receiving a request. But I want to stick on this slide for just a second and note at least that here, although some of these numbers seem pretty big, like 358 or 556, we're soon going to see an example of attack where the amplification factor was way off the scale compared to all of these previous amplification factors. So let's talk about a sort of infamous attack that left Akamai with a bit of a black eye. So there's a famous security blogger named Brian Krebs, and his blog came under attack on September 20th, 2016. And at the time, it was the largest attack that had ever been seen in terms of gigabits per second. Krebs had previously been given pro bono or free protection on the Prolexic network prior to when Akamai acquired it. And it's not really known why his blog was attacked or who attacked it, but it may not be coincidental that he had previously posted something about a website called VDOS, where you could go to purchase cyber attacks for a fee, and then after his post, several people were arrested, and sometime shortly after that, his blog came under attack. Now, what happened next was this huge volumetric attack that was more than Akamai had ever seen before, and after 2 days, Akamai booted him off the network. Okay, and that was, to me, was kind of embarrassing. Now, there's a bit of a cover story that, hey, we were doing this for free, and this kind of thing adds up. We typically, when we buy bandwidth, we're paying for it on a 95.5 basis, which means over the course of a month, they look at each 5-minute interval, and they sort them at the end of the month, and they bill you at the 95th percentile. And so if you use more than a day and a half's worth of bandwidth, all of a sudden your 95th percentile becomes very large. But that's not really the only reason he was booted off the network. The attack was so large that it was impacting all the customers in these Prolexic data centers. Afterwards, I asked, well, it's just a website. Why didn't we move the website onto the CDN? Which they could have done. And one of the interesting responses I got was that, well, in some of these Prolexic centers, the pipes were completely full. So that even though we measured it at, this one was, 700 megabits per second, something, or gigabits per second, we really don't know how big it was, because if we had had a bigger pipe, we might have let in even more traffic. And so they were reluctant to do that. Google kind of saved the day here. They also have set aside money and server capacity to protect free speech. And they, a few days later, took the Krebs blog onto their platform. Here's another interesting attack. It happened just in March of this year. It was launched against GitHub. And it was sort of a new attack vector. It used the fact that there are tens of thousands or possibly even hundreds of thousands of memcached servers that are open on the internet that let you do things like store a bunch of data and then send requests for data with spoofed source address packets. And the memcached server will then start blasting the data using UDP to the source address. And people have demonstrated an amplification factor here of over 500,000. Like you can preload some data into the memcached server, and then sending a single 208-byte packet, get it to send back 103 megabytes of data, uninterrupted. So that's bad, considered bad. And so they did this to GitHub. GitHub went down for 10 minutes, and then they had made some arrangement already to be able to switch over to start advertising a Prolexic IP Anycast address, and they did that. And so this graph shows the ramp up of traffic on Prolexic once GitHub switched to using Prolexic. And what's interesting here, and it's a phenomenon we see a lot, is that, okay, first of all, by now, after the embarrassment of what happened with Krebs, a huge amount of additional bandwidth had been added to Prolexic. So by this time, there was no problem handling an attack of this magnitude. And it ramps up very quickly within just 2 minutes to 1.35 gigabits per second. And it sits there for another 2 minutes, and then the attack tapered off. So what we've often seen is that when attackers are expending a huge amount of resource and they can see that it's not having any impact on the service, they quit. There's no point in wasting your resources. And so this was a successful mitigation There have been a handful of other attacks now of about the same magnitude. Somebody earlier this morning mentioned the attack against the Doan DNS service provider. Sort of comparable, using that was using though the Mirai botnet instead, which was what was used against Krebs. One of the things about this attack that made it relatively easy to mitigate was that all of the attack packets came with the same UDP source port, 11.2.11. So it's very easy, even just in the routers in the data center, to say, okay, we're just going to throw away everything coming in with source port 11.2.11. Didn't have to do anything sophisticated. Turns out that that was a decision that was probably made a little too quickly, and there was a little collateral damage, but it kept GitHub alive. So now I'm going to switch gears and talk about web application attacks. So the first class was sort of just brute force attacks, but we also see attacks where the goal is to take advantage of vulnerabilities in applications. And one of the reasons why this matters more to Akamai now than it once did is that there's a trend towards using CDNs for full site delivery. In the earliest days, Akamai did fairly simple and maybe kind of even stupid things. We served images, we served videos, we served software downloads and documents, but we didn't as often serve the whole web page. That's changed, and part of the impetus for the change was a series of attacks in 2012 and 2013 by a group that called themselves the Kassem cyber fighters, who launched Operation Ababil against US banks. And after that happened, the banking industry moved to having their public online presence delivered entirely through CDNs. It was already the case that government websites like the White House website had been going through CDNs. Since then, a pretty high percentage of, say, Alexa top 500 websites are also going through the CDNs. One of the consequences of this is that because these sites are also all switching to TLS, the CDN has to hold the private keys for these websites. So nowadays, when you sit down and you connect to your bank, there's really no indication that you're actually connecting to an Akamai server or perhaps some other CDN server. But that's what's really happening. So we're seeing all of the HTML traffic passing through our servers. It gives us an opportunity to interdict in some instances when an attack is taking place. Whereas before, in the earliest days, those kind of interactions between the browser and the server where anything interactive was taking place happened directly. Now it's all passing through the CDN, and the CDN is decrypting it and seeing what's going on. I should say that another motivation for doing this, for using the CDN as a sort of a forward proxy, is that it can also reduce latency. And so Microsoft's Bing search engine was one of the first to use Akamai as a front end for all interactions, even though Akamai can't do any search at all. We don't have any information about what the answer to some query is, and we don't cache the answers to queries. But the idea was that the end users' browsers would make connections over low latency paths to nearby Akamai servers so that the CCP three-way handshake and slow start and all of that would happen more quickly. And then the Akamai server would maintain a long-term persistent connection back to the customer's back end, and maybe even use an overlay network if the default route wasn't the best. So this trend is happening. Full site delivery through CDNs, and CDNs are getting in the business of helping protect against attacks. And so this is a picture of what's called Akamai's Kona Site Defender, used to be called Site Shield. Oh, by the way, this reminds me, I'm in deep trouble with Akamai because I didn't have time to change the slogan on my slide. See, it says faster forward. So for years, I've been lobbying against faster forward as being Akamai's slogan because there was this competitor company called Fast Forward that was started by Steve McCann and eventually bought by Inktomi. And I'm like, is that really the best we can do? Faster forward? Okay? They're fast forward, we're faster forward. But I'm here to reveal to you today that we, as of this week, have a new slogan. Experience the edge. Okay? And before anyone snickers at that, let me just say that at least it's not as bad as our first slogan, which was serving web kind, period, intelligently, period. Okay, if you can get an Akamai hat that says that on it, that's considered a real collector's item. Okay, so how does this work? So it's similar to the Prolexic system, except we don't use IP Anycast. Okay, we use DNS as the redirection mechanism for sending clients to Akamai servers. We don't have just a few dozen locations, but we have thousands of locations around the world. And, but otherwise, it's sort of similar, except that oftentimes the content can be cached. And so when a request comes into a server, an answer can often be sent back immediately. Okay, that's the traditional CDN caching service. But then there are also some requests that come in that can't be responded to from the cache, perhaps because the content is dynamic and it requires a response from the server, and so the request may be passed back to the server. This may be an example where we keep a persistent connection open to the server, or in some instances we may tunnel the request back over an overlay network. And now the servers are also going to bear the brunt of attack traffic. And it's always been the case that if anyone focused enough attack traffic on one server or one server installation, they might be able to take it out. But there are so many of them that the DNS will just stop giving out that location, and the user will be sent somewhere else. So that's the idea behind this system. It has a lot more capacity. And we'll talk a little bit about what it does to try to mitigate attacks. One of the things it does is rate limiting. So different customers will tell us what they think a reasonable rate of access is for one of their end users. Like a bank would say, we don't think that we're going to be getting 10 requests per second from an individual. So if you see that, it's okay to throttle them. You know, not necessarily block them, but slow them down. So rate limiting is one of the things we do. I'm going to show you a bunch of data about the types of application layer attacks that we see. And one thing I wanted to impress upon you is that when we collect this data, we're not totally naive. So we understand that there is a lot of automated survey machinery out there, different services that go and scan looking for vulnerabilities. And Akamai actually has a very sophisticated bot detection mechanism in place. One of the things we're constantly doing is trying to understand what traffic and what portion of traffic that we serve is going to real users and what is going to bots. So just as a baseline, for all of these legitimate scanners that are looking for vulnerabilities, we can they're easy to identify. We take them out. None of the attempted vulnerability checks that they do appear in any of our data. So, oh, that's a little unfortunate. It's hard to read the attack types here, but if we look at them, the number one category, this is in Q4 2017, was an SQL injection attack, and then we have local file inclusion attack, and then cross-site scripting attack, and so on. So these are all well-known attacks that people launch against web servers. I think this audience may have some familiarity with these attacks already. I'm going to just briefly describe an SQL injection attack because it's the most common. And so, let me say something about who the targets are. What's interesting is if you break down the type of websites that are attacked here by industry, you see something that's very different than you saw with the brute force DDoS attacks. So for example, gaming isn't there anymore, right? Because those were gaming servers, they weren't websites. So we're seeing more attacks mostly against websites where there are customers that are doing business with the site and buying things. Okay, so real quickly, here's what an SQL injection attack is. So SQL stands for Structured Query Language. It's sort of one of the older and most common ways of interacting with a relational database. A relational database is just a table that has rows and columns. Here's a table of employees, and each row corresponds to one employee, and you have columns that hold different attributes of the employees, like their first name or last name or salary or whatever. And if this was stored in a relational database, like an Oracle database, something like that, you could issue an SQL query like select star from employees where L name equals Parker, and what it should do is return that one row with the information about the employee named Parker. Now, let's say you built a website and you have a form on that website where you ask the user to enter some information, and then you're going to have maybe some Java servlet code that's going to take whatever was provided in that form by the user and craft an SQL query and send it to the database, and then take the results and display them on the web page. So let's say that there's some code, and in this code, this is, say, some Java or something that's creating this query. There's a variable called username that's being filled in by whatever somebody types in a form on the web page. And so you're expecting somebody to type something like Parker, and then it's going to display the row for Parker. But instead, somebody types this. Quote or quote one quote equals quote one. Okay, now that's crazy, right? But what happens when you look at the query is it says select star from employees where L name equals empty or 1 equals 1. Okay? Well, 1 is always equal to 1, so what is going to be the output of this query? All the rows in the table, right? So that's kind of the standard SQL injection attack. So the CDN now does something for the customers, which it does just sort of applies a standard set of rules that do basic sanity checking on the inputs to make sure that this kind of string doesn't get passed up to an application server somewhere, right? So that's a common thing. The whole reason I introduced this, though, was because my all-time favorite cartoon is based on this. How many people have seen this cartoon before? Okay, it's just great. So the mom gets a call. Your son, this is your son's school. We're having some trouble. Oh dear, did he break something? Did you really name your son Robert, quote, right paren, semicolon, drop table students, semicolon, minus, minus? She's like, oh yeah, we call him little Bobby Tables. Okay, this is fantastic. I get calls about my son sometimes, but they even send a helicopter looking for him in the woods one time, but that's a different story. I'll just say that in Chapel Hill, you shouldn't carry a BB gun around in the woods. Okay, so last topic. So I talked about web application attacks, SQL injection attacks, local file inclusion attacks, etc. But actually, probably the largest scale and the most pernicious of the attacks we see are malicious login attempts. We see over and over again campaigns to try to log in to accounts at banks and travel industry websites and elsewhere. And in most of these cases, they're trying to log in to websites where usernames are email addresses, and the attackers tend to collect very large files of username or email address password combinations, and then they try to see where they can log in. And the Akamai servers look for failed logins or multiple logins failing one after another from the same client. And the scale is a little hard to see here, but we're logging tens to hundreds of billions of malicious login attempts per quarter. So it's a huge thing. And this is one of the things that we try to mitigate. And I'm going to talk about a campaign that was based on some compromised Internet of Things devices. So some attackers got put together somehow a huge list of username password combinations. Okay, don't feel bad if yours is on here. It probably is. And then they took advantage of some different home routers that they were able to, my kids would say, pwn. Okay, they took over these home routers, and then from each one, they tried to log into a banking website. And what was interesting about this was they took this file, which had many millions of email password combinations. They split it up. They sent it out to these routers. And then they had the routers slowly try to log in. And if we look at the attack, over a period of 10 days, they tried to log in from over 1 million distinct IP addresses, and they tried 427 million login attempts. And so that's huge, but if you do this over a 10-day period and you've got 1 million, say, devices, each only doing 400 login attempts, that ends up only being between 1 and 2 per hour. So you can go very slowly, try to stay under the radar, and still launch a massive attack. So we kind of see this 2 modes in which sometimes botnets like the Mirai botnet are used to launch sudden, massive attacks aimed at denying service. Other times, the scale is used so that even though the attack is very large, it can be done under the radar. Yeah, so 75% of them were observed to keep attacking day after day. Okay, so a few observations. First, and this should be no surprise, it doesn't really make sense for the provider of an online service, unless they're really, really, really big, to provision for that rare day when they come under attack. It's just too expensive. The size of the attack may be tens of thousands of times larger than their typical traffic. And so for that reason, they'll turn to the small number of companies who dedicate infrastructure to preventing attacks. These attacks happen very quickly. They can ramp up very quickly. You saw what happened in 2 minutes in the attack on GitHub. Sometimes relatively small bot armies can generate large attacks. So this can happen when there's a vulnerability with a large amplification factor. Occasionally, Akamai sees attacks where somebody has gone out to bulletproof hosting companies, which are like data centers often advertised in Russian, where they promise you that no matter who complains, they won't shut off your network connection. And even with just a few thousand servers, you can generate quite a large attack. But nowadays, the really large attacks tend to more often come from these really large bot armies that can consist of, hundreds of thousands or even occasionally several million different hosts. So I think I'm doing fantastically well on time. I'm going to stop there. Welcome any questions.
We have time for a few questions. Are there any questions?
Yeah. I think we have that information, but I don't have it. It's much smaller than the number of failed attempts, but I don't have it with me. Yeah, it's much smaller, especially when you're talking about hundreds of billions of failed attempts. There just aren't that many people logging in for it. You know, it's yeah.
So I'll ask a question on what you mentioned how the slogan has changed towards the edge.
Experience the edge.
So how does security change the edge, or more specifically, how are your defense mechanisms for DDoS going to change now that we're all trying to experience the edge?
Well, that's a good question. You know, what's interesting is that the Akamai's infrastructure, the one that's dedicated just to security, Prolexic, is not at the edge. Although it's distributed, it's not very well distributed. And part of that is because the IP Anycast mechanism, people are concerned about what would happen if you tried to put the same Anycast address for TCP connections in more than a few dozen places. So that there's a question of how do you even push that to the edge. Now, I've asked at Akamai, well, why are we using Anycast? Why don't we try to put everything on DNS like we do all the web services? And the answer is that this is sort of a generic service where people will come to us and say, I want every service in this data center to be wrapped up. And there's no possible way that they can go and change them all so that they can use a different DNS system to direct the end users. So it's because it's sort of a general purpose black box, it's somewhat centralized. It would be nice if more of the security functionality could be pushed down into what's really truly an edge deployment, the Akamai CDN itself. It would also be nice, in my opinion, if Akamai would sort of go for a moonshot and increase the number of physical locations from the current 3,000 something by another factor of 10 to 100. We're not really at the edge. We say we're at the edge. We say that we're one hop away from 80% of network devices. But if you look at the histogram of latency between Akamai servers and clients, it's in the, you know, it's not, there are not enough of them under 10 milliseconds. We're not close enough to the edge.
Okay, we're actually running way over now. So let's thank our speaker. next for this is going to be Varun from University of Wisconsin, and this whole session is actually home networking, basically making home networks more secure. And so we will talk about some work that they've been doing to try and help us better understand privacy within smart homes.
So I'm going to start off by apologizing in case some of the animations are off. I had my slides on Google, and well, clearly I can't really access them. The keyboards are in Hungarian, so I couldn't enter my password. Let's get started. My name is Varun Chandrasekaran, and I'm a doctoral candidate at the University of Wisconsin at Madison, advised by Suman Banerjee. I'm here to present our proposal on preserving privacy in your smart homes, specifically from the many smart speakers or voice assistants that are being used today. Okay, awesome. So this is a picture from Studio C. It's a popular YouTube channel. The young man on the couch is trying to reach the Coke can with a vacuum cleaner. It's a very random picture to start off the presentation, right? Well, it's to suggest one important thing. We're always on the lookout for more convenient solutions to our problems. I don't know if this is very convenient, but what best captures this fact? The emergence of voice as an interaction medium between users and devices. They're being used pretty much everywhere. We talk to our smartphones. We have smart toasters now. Yeah, that's a thing. I don't know what they're used for, but we talk to the gym, the treadmill in the gym, smart TVs, and smart watches. So the Internet of Things and the devices spawning are becoming increasingly pervasive in our homes. Let's take a look at two images. They look like they're pretty much the same article, right? The author is Sarah Perez. They're on TechCrunch. Well, they are. It's just that they're 2 months apart. So it's amazing. In 8 months, there have been close to 8 million smart speakers that have been added to American homes. Can you imagine the number of pizzas that we can order without typing in anything? It's cool. Okay. But there's no free lunch. Recall how these smart speakers work. They respond to hot words followed by a voice command. These are clips from various news articles that suggest that these devices are always listening, even when we don't explicitly use the hot word. What's worse is that the speech needn't be from a real person in that room. It can come from a conversation you're having over the phone or some dialogue occurred on TV. I'm sure some of you have experienced this too. So you're probably thinking, why does this matter? I've got nothing to hide, and even if they are listening, what's the big deal? Well, this could happen to you. Your private conversations could be recorded in your home, and could possibly be shipped to your boss, even your mother's. Well, this is a funny story I'll tell you later. Or this. There's a bug in Google's code that could enable them to record and eavesdrop your conversations. This raises our first problem, innocuous recording. These smart speakers are capable of recording your conversations without you knowing they're doing so. Recall from an earlier slide where someone spoke something on TV and Alexa went crazy. This is a consequence of voice being an open channel. Several academic works have exploited this fact to create apps that generate malicious commands, inject commands through human inaudible sound, it's the second box, and modify a legitimate user's voice such that it produces some nasty outcome. The broad theme of these forms of attacks points towards unauthorized or unauthenticated use. You shouldn't be able to walk into my home and use my smart speaker. Better still, you shouldn't be able to sit in a car outside my home, inject some sound waves to control my smart speaker, maybe asking it to open my garage. So some of you might be thinking, voice biometrics might solve this problem entirely. The high-level idea behind voice biometrics is there are some unique characteristics that can be used to identify a person. Maybe this can even be combined with some form of passphrase that only you know. Some of you might have used voice-based biometrics to identify and authenticate yourself to your bank. But there's a bunch of academic literature that suggests that this is not strong enough. So let's take a breather and recap some of the problems we've discussed so far. These devices are capable of performing innocuous recording, and there are always unauthorized users in the operational ecosystem. So in some sense, we have two adversaries that we're targeting against, the smart speaker itself and the unauthorized users. Does this mean that if we care about our privacy, we have no future with these smart speakers? That's not true. I mean, and if you're curious, there's this popular street artist called Banksy, and he makes these murals on streets. Source of this image. Well, that's not entirely true. We do have a future. We can do a lot better, but we have 3 challenges to overcome first. Yeah, I want my smart speaker to listen to me only when I'm communicating with it, which naturally means that it should not be listening to me when I'm not communicating with it. So how can I achieve this? I can jam the smart speaker, say with some really harsh noise. But as an end user, I shouldn't be able to hear this noise. It's really irritating. Or I shouldn't even know that this is happening. Now, if that's the case, how do I preserve legitimate access to the device? A jammed device should be able to identify my voice commands when I say, hey, Alexa, play me some music, please. Finally, any malicious entity in this ecosystem should not be able to successfully record and replay my commands. This is the fundamental shortcoming of voice biometrics. It's susceptible to replay. Cool. So let's look at the smart speaker system in the status quo. I can issue a voice command and the smart speaker responds. Great. This is what's supposed to happen. Now some malicious entity can also issue a voice command and the smart speaker responds. This is not supposed to happen, but this happens anyways. Sometimes I don't even issue a command and the smart speaker responds. Or worse, it records what I'm saying. So our proposal is to intelligently obfuscate the smart speaker. To do so, we need 2 new pieces of hardware in this ecosystem. The first new piece is the obfuscator. Think of this as some form of trusted hardware that the adversary can't compromise. You can buy it off, let's assume that you can buy it off the rack at Walmart and you believe that it's doing the right thing. Better yet, it's not connected to the internet. This device generates some form of obfuscation signal to jam the smart speaker from recording. Now the user issues a voice command to this obfuscator. To prevent unauthorized usage, the user also has to authenticate herself with the obfuscator. The user does this using some hardware token, which is the second new piece of hardware, using a secure side channel. Okay, so great, awesome. When this is done, any command spoken by the user is processed as follows. The obfuscator first detects the hot word spoken by the user. Then it begins to stop obfuscation. Now any command uttered by the user is replayed directly to the smart speaker. So let's go back to some of the challenges that we have to overcome. This obfuscation signal should be human imperceptible. So what do? It's quite simple, just use ultrasound. The obfuscator generates ultrasound. This is inaudible to the human ear, but is audible to commodity microphones, including those in Google's and Amazon's smart speakers. Okay. The reason this is possible is because microphone hardware experience nonlinearity beyond the cutoff frequency. In this example, the obfuscator plays 2 ultrasound tones at frequencies F1 and F2. They are not recorded directly since individually their frequencies are beyond the filter's cutoff frequency. From the equation below, observe that apart from the linear term V in, there's a nonlinear term V in square that also exists. With simple mathematical transformations, we see 2 harmonics with frequencies F1 plus F2 and F1 minus F2. The F1 plus F2 term is filtered out, along with the terms that compose individually of F1 and F2. But the F1 minus F2 term is recorded since its frequency is below the filter's cutoff frequency. We can play with the values of F1 and F2 and decide what is being recorded by the microphone. Since the human ear does not have this kind of nonlinearity, it cannot hear F1 and F2. Great, so we're able to obfuscate this device and prevent it from listening to what we talk about. But this raises an important problem. It also obfuscates legitimate voice commands that we're issuing. So we can't use Alexa or Pizza or Domino's anymore. So one strawman solution is to equip the obfuscator with a microphone such that it is capable of detecting the hot words we speak. Once we detect these hot words, it can consequently stop the obfuscation. But the problem is that the obfuscator's mic will also be jammed by the obfuscation signal that is being generated. So how do you detect under obfuscation? Simple, use an ultrasound microphone. Cool. Negligible nonlinearity exists within the operating frequency range of the ultrasound mic. In this example, the cutoff frequency is beyond F1 and F2, so there exists no V in square term. And the microphone does not record any F1 minus F2 term, as in the previous equation. The hot word, which lies in the human frequency range, lies at a much lower frequency than either F1 or F2, and can easily be separated by digital filtering at the obfuscator. So we're recapping what we've discussed so far. The user utters a hot word while obfuscation is still active. The ultrasound mic is able to process the hot word, and this stops the obfuscator from jamming the smart speaker. Now the end user can issue her command. The final challenge we have to overcome is resilience to replay. Let's go over the typical replay scenario. There's the user, smart speaker. Now the obfuscator, which is generating some sort of obfuscation signal. The user issues some command like, Alexa, open the garage door. The microphone records, microphone detects the hot word, proceeds to stop obfuscation. Great, all is well in the world. Okay, but now assume that the user is kind of isolated from the smart speaker, and there is a malicious party in this ecosystem. Somehow this malicious party is able to record the user's command. D is missing, apologies. And replay this command to the obfuscator. Now the obfuscator stops obfuscation. This doesn't seem right. The replay example is an instantiation of unauthorized use. To ensure user authentication, we don't use voice-based biometrics, as I mentioned before, because they're also susceptible to replay. Instead, we use a different approach. We use hardware tokens and combine it with physical proximity to the smart speaker and the obfuscator. So the user is in proximity to the obfuscator, deactivate obfuscation, else continue jamming if the user is not close to the obfuscator and the smart speaker. Why does this make sense? People don't really shout at their smart speakers. They are quite close to them when we communicate. A simple way of determining proximity is to equip the obfuscator with a range-controlled Bluetooth transmitter. Assuming the user always carries their smartphone, we know that if the user's smartphone is near the device, then the user is too. So this is what this diagram is supposed to encapsulate. So there's the user's smartphone. It's also always transmitting something on Bluetooth. Obfuscator has some Bluetooth. We determine proximity. If the user is far away, since the Bluetooth is range controlled, it's just not going to work out. The obfuscator always issues some form of challenge, and when it is met with a response from the user's smartphone, it ascertains the user's proximity and stops obfuscation. More details of this challenge response protocol are in the paper. So let's go over the complete workflow. In the first stage, the obfuscator issues some form of challenge, which is the lowest row. Once this is met with a response, great, the user can issue a hot word. Then obfuscation is stopped, which is indicated by the green in the last row. The user can issue their voice command. Once the user stops their voice command, there's some period of silence, which is noted, and then obfuscation resumes. So then this child response protocol continuously goes on. So at a high level, this is our proposal. For future work, we want to study how the scheme will apply against an adaptive adversary, one that is aware of what we're doing. Such an adversary could perform beamforming. Worse, since there are many devices made by the same vendor, these devices could collude and determine where the source of jamming is. We don't know how our scheme is going to perform in such context. We want to understand how the scheme will apply when we have multiple users in a home with conflicting privacy requirements. While I love my privacy, not everyone has to feel the same way. How does our authentication mechanism fare against an adversary that is aware of specific timing information related to when the user is authenticated? The adversary can specifically inject sound then. It's far-fetched, but we have to cover these corner cases. Most importantly, we want to know if users will use such a solution to begin with. So we've prototyped this, and we're conducting user studies as this talk's going on. So thank you for your time. And if you have any questions. Please. Yes, so since there's like a microphone array, because you can communicate with your smart speaker from any direction, positioning it is very important. So we found that placing it on top of the smart speaker is probably the best. Yes. Yes. It's not, well, it's fundamentally like, so it's not connected to the internet in any capacity. So by definition, no longer IoT. It's not really doing anything fancy for you to update, right? It's just generating ultrasound. Byte once, yes. Configure it once, yes. No, it's just generating ultrasound. So, yeah, exactly. Yeah. Yes, sir. So again, so the user is at home, which means, so the assumption is the user has their smartphone with them. So if the if it's the user and the smartphone are not near their smart speaker, then the smart speaker is going to be jammed. So there's this very small case where the user and their smartphone are near their smart speaker, and at that point in time, replay is going on. Yeah, it's a good question. We don't have a very smart solution for that yet.
Let's think. Oh, sorry.
Yes. Yes, but then you have to trust Amazon or Google to do the right thing. Now you're right. You're right. But again, this is a fundamental, like I think, qualm that all privacy researchers have, which is, do you trust these organizations to do the right thing? Like they can say there's a bug in their code, and this is why they're not doing this, or are they actually doing it? We never know.
Let's thank our speaker.
Thanks.
So our next speaker is Doan from University of Calgary, Canada. He's a master's student. His research interests focus around security and privacy of IoT devices, surprising. And he's going to be giving us an interesting talk, basically transferring from privacy back into security, kind of looking into still the home networks, but how do you secure home networks against different types of attacks? And one kind of very cool thing about this is a lot of the reviewers like the systems aspect of this paper and like the aspect of the techniques and how they actually help you in terms of fixing a lot of broken issues that exist right now. And so what I'm trying to say is this is actually going to be the best paper. It has a lot of interesting, cool ideas, and you guys should take notes and ask very hard questions afterwards. With that, thank you, Theo.
Hello, everyone. So I will present the paper for our group. Um, the paper title is Toward a Resilient Smart Home. And the first slide, I just want to remind about the Internet of Things. Kevin Aston, who coined the term Internet of Things, and here's the extract information from his journal. And we can see that we don't have the specific definition for Internet of Things, but we can also explain it as like a computing concept that everything is connected to the internet and can be able to identify themselves with others. And the smart home. So the smart home is the contain 1,000 of the device that be connected and communication inside the smart home. The goal of this is give people the smart living, like for example the smart lock that the user can lock or unlock remotely, right? So because the role of the Internet of Things lead to the benefit of the smart home. Currently, they have a lot of the cloud-based smart home. We can see is the Amazon AWS, IBM Watson, or Apple HomeKit. So our questions, our motivation question is because currently smart home platform is cloud-based. So what happens when the cloud is disconnected? Currently, everything is rely on the cloud. So when the cloud is disconnect, the reason the cloud is disconnect or unavailable is because of technical problems or natural cause. It will give the home users unsafe environment. For example, if the thermostat stop working at night, the smart one can make the house really cold, right? So we first investigate what happened, what is the reason why the cloud is unavailable, and then what is the effect. The reason the cloud is unavailable can be like technical problem, natural cause, or even for security, the target attacks. The effect is it will break down the home security system. The most important thing is for home alone users, for example, like old people, older people, they need to wear the smart sensor all the times. So if that stop working, it's really take risk. So the goal of the project is to investigate and then to introduce the infrastructure that can be take over the house when the cloud is unavailable. So the first step, we need to analyze the essential service in a smart home. What is the essential service? This is the service need to be maintained, working all the time during the cloud is disconnection. So we classify it in different aspects for healthcare, security, or storage, and connectivity. As we can see a detail in the table. So the next step, we introduce the Resilient Smart Hub. This is the hub for the smart home. We call it REST Hub. So the goal of the hub is to provide the functionalities of the essential service during the periods of the cloud disconnection. The hub needs to maintain at least 3 functions, like detection of the cloud unavailable, send a notification to the user, or do the service transfer. It means take over the control of the device inside the house during the time the cloud is unavailable. So the challenge here is how can we make REST Hub control all the device in the house? Because currently in the market, if you buy Samsung device, it can only be controlled by the Samsung Hub. If you buy Apple HomeKit, it can only controlled by Apple. So we're looking at the IoT VTIF. So IoT VTIF is the open standard from OCF. OCF is the Open Connectivity Framework. So OCF provide IoT VTIF in the case that it will be the future standard. It can be controlled on the device in the house, rewriting, doesn't matter like the manufacturer, the operation system. So this is the IoT VTIF software framework. So depend on this software framework, we will introduce the REST Hub architecture. So REST Hub is mainly based on the IoT VTIF framework. And we can see here we have three applications. We have three layers. The application layer, common service layer, and the network of things layer. A quick look at the network of things layer, we have resource observation. This is the virtual device, like it's present for the device connectivity. The network connectivity is the physical connectivity using wireless or using wire. In the common service layer, we have the service security and we have the resource management. This is the middle layer. This is the most important layer inside the framework. So now we introduce the REST Hub software architecture. And we can see for each layer, we have many different modules. Depend on the service, in the essential service, we have the corresponding like module. For the connectivity technologies, instead of the core protocol using in IoT VTIF, now we use MQTT over TCP/IP. The MQTT module is on the layer 2, and we can see it. So now we have the software architecture for REST Hub. The next thing we consider is the security. The secure access and control of the home device. So the goal is when the cloud disconnection, this provides the windows for many attacks. For example, the attacker may not be outside the house, but maybe the incident in the house. Like the landlord have many tenants, so he set up the restriction room. But when the cloud is unavailable, this room can be opened without the permission from the owner or the landlord of the house. The challenge here is we need a stricter set of security requirements to do authentication and authorization for everything in the house. So for all the protocol, we choose OAuth. OAuth is the open standard for delegation access. As we can see nowadays, like Facebook or Google, they use OAuth. We try to adapt OAuth with MQTT. MQTT is the publish and subscribe protocol. An example of the subscribe request. So the first step is the MQTT client want to subscribe to the topic at the broker. they need to send a request. And the broker need to ask for the access token, authentication, and then when the client, the MQTT client have the access token, it can subscribe to request the message from the topic. We also give out the roof of implementation. So this implementation demonstrates that REST Hub have ability to take over the essential service inside the house. On the red table is the component we use for implementation. Why we choose Samsung SmartThings Hub, Samsung SmartThings Smart Home device in this case, because Samsung SmartThings use the physical hub. So we first try to take over the control of the hub, the physical hub, and then for others, IoT platform, they use like virtual hub. This is the component for the implementation. So we have the SmartThings Hub, we have the Smart LED bulb and the LED bulb, and then we have the SmartThings motion sensors. So the goal is the LED bulb and the motion sensor will generate the message. And the SmartThings Hub will collect the message and push the message to the Samsung cloud. So the goal is REST Hub need to be collect the data directly from Samsung cloud and analyze the data to be repaired for the cloud disconnection. And then REST Hub will detect when the cloud is disconnected, and using the data already collected, this will take over the control of the house. In the meantime, we just implementation 2 modules. The first is the resource state synchronization module. So the task for this module is just collect the information when the cloud is still available. And this information will be stored in the database for further processing. For notification module, this module is respond for send user the notification when the cloud is unavailable and also when the cloud is available. It needs to transfer the service back to the cloud. This is a demo of experiment from SmartThings. As we can see, right here, this is the lab, generate information and the motion sensors. So all of this information, REST Hub need to be collected and stored in the database. For the future work, actually, our paper is the first step in providing the resiliency for smart home. To require further research, a small device and service to enter in the house. And we need to call for collaboration with smart home providers to refine the APIs and access to their system. This is the one important point because currently the smart home provider are not interested for local processing. So whenever you bought the smart home device from any provider, you need to trust them. Any information generated inside the house will be collected and processed in the cloud. So the privacy is really an issue. And we need to evaluate this design and expand more threat model for security. If we can have the physical REST Hub in the future, it would be great. Thank you.
We have time for a few questions.
Yes.
So if we go back to your authorization diagram, it looks like there's one last
This one?
client authentication. That typically is
Yep.
it requires the cloud service or cloud connection to do that last part, right? So if you let's say you come back home, you have your phone, you don't have any, you lost cloud connectivity, and now if you want to get that client authentication, you're gonna.
So you mean the secure resource manager need to be in the cloud, right? Everything is as we can look at the module here. So in the common service layer and even the network of things layer, everything in local. So we build our own local system for like giving the management, the certificate and everything.
So you have the whole authentication
Inside the house. Yeah. Because if we put the authentication in the cloud, we need to trust the cloud provider. So the goal here is we have the local processing, so the users in the house can keep track of everything inside the house. Yes. Okay, for the first question, like, so how can you see the integrity of on the message from the device? That's why the REST hub is, so the REST hub collect all the information generated by the device from SmartThing Cloud, and then we have the secure event log, we sign on the message, and we keep track up in the database. So after that, we can verify if the message is tampered or not. We have we actually have a publication about the secure event logging. So we build the event logging system using cryptography to do the privacy for the message integrity and everything. As we can, I can discuss with you about that later. Okay, I got it. Yeah. So that is the goal. We need to evaluate the whole system, and we need to have the real data streaming between the device, and we can verify if actually how secure is and how integrity is the message.
So one question, kind of going back to the first couple of points you had, this whole idea of mod.
Yeah.
And it kind of provides this mechanism for the vendors to provide signatures that get enforced. So how do you see mod playing a role with your REST hub architecture?
can you just repeat?
So the mud techniques that were discussed previously about creating acceptable device signature, like how should this device behave? The vendor creates it, pushes it down, and then essentially maybe an SDM controller or an IDS uses this to enforce rules. How do you think that view of applying security would work next to yours?
We actually didn't look at it yet, but I can consider it. Like, because the main thing here is we try to provide resilience first, and the security part can be a stand, because first we need to evaluate the system, right? Thank you for your.
Okay, let's thank our speaker.
Thank you.
All right, so the speakers from the next session, I have your USBs already, or I have your slides on USB, but can you come up so we can go through your slides and make sure they will appear correctly? And now it's lunch, so we'll start again the next session at 2 p.m.
Good afternoon, everyone. Welcome back. I'm Bala. I'm a senior researcher at the Max Planck Institute for Informatics in Saarbrücken. I'll be chairing this session on security. In my opinion, actually, this is the most interesting one for today because although it's just titled security, it starts off with a very interesting paper that shows how you could take control of IoT devices. And the next one that talks about how to detect who the attackers are. And the third one, a very clever way of protecting the end users. So I'm very excited about it. And so let's invite our first speaker for this session. Our first speaker is Frank Lee. He's a PhD student at the University of California, Berkeley. He works with Professor Vern Paxson. His research is primarily on understanding and overcoming the barriers that prohibit users from remedying security issues such as misconfigured systems and outdated software with vulnerabilities. The interesting thing is, if you look at the publications that Frank has, what you realize is that he seems to have gotten tired looking at measuring, all these vulnerabilities. And to educate users, he's now going to start attacking, these devices. So with that, Frank, go ahead, tell us what you have.
Great, thank you for that introduction. So good afternoon, everyone. Hopefully you're not too sleepy from after lunch, and I can try and keep you awake. So again, my name is Frank Lee. I'm a graduate student at the University of California, Berkeley. And today, I'm going to talk about web-based attacks against local IoT devices. So this is joint work with a number of great collaborators who are part of Princeton University's Center for Information Technology and Policy. So as I'm sure everyone is already well aware here, there's an ongoing wave of these consumer IoT devices that are transforming user homes into smart homes. But these devices are also designed often without security in mind, and they're riddled with various kinds of security vulnerabilities and misconfigurations. Now, while these devices have the opportunity to, transform and potentially significantly improve people's lives, they also introduce arguably hundreds of millions of potential new targets for attackers. So as we continue with this IoT movement, we need to carefully consider the consequences of deploying these IoT devices. And in particular, to that end, it's important that we understand how these insecurities in the devices can potentially be leveraged by an attacker. So for an attacker to actually trigger some of these vulnerabilities, they need to be able to reach the IoT device. So how might they actually reach the devices? Well, some of the devices are actually just publicly accessible. For devices that are on a home network that may be behind network address translation or NATs, port forwarding can make these devices publicly visible and potentially accessible to anyone on the internet. And we've actually already seen a very significant attack on publicly accessible IoT devices last year with the Mirai botnet, where hundreds of thousands of these publicly accessible IoT devices like cameras, DVRs, baby monitors were compromised and used to launch one of the most devastating DDoS attacks that we've ever witnessed. But the majority of IoT devices are actually still not publicly accessible, and they sit behind NATs. So how can an attacker actually get to them? Well, one way is through local malware. Say, for example, if the attacker infects one of the local hosts on the local network, then it can laterally move and attack other local devices. And this is certainly a very feasible route because we've seen that malware infections are quite rampant in practice. However, there's actually arguably an even easier way, which is what I'm going to talk about today, which are web attacks. So for those of you who are unfamiliar with web attacks, let me kind of give some context. So unfortunately, this didn't show up very well, but imagine that you had your local network and that there's some IoT devices such as that Wemo switch. And then there's also a browser running on a user's local machine, such as their PC. In a web attack, the attacker convinces the victim to visit a malicious website. So there's now a malicious website running in the browser. And then this malicious website, as I'll kind of talk about today, will be able to attack the IoT device. So this is really a very low bar for the attacker because there are so many different ways we can get somebody to visit a website, whether it's clickbait, spam emails, social media, anything like that. And arguably this is a much lower bar than even compared to malware. So today I'm going to talk about two different types of attacks, web-based attacks. The first is to identify other local IoT devices on the network. And the second is to potentially access the data exposed by these IoT devices and potentially control some of their actions. So really the goal of this paper is to kind of inform our understanding or our mental model of what are the threats against these IoT devices, even when they sit behind NATs. So before I get started talking about the attacks themselves, we need to understand what are the attack surfaces against these IoT devices. So because this is a web-based attack, the attacker is ultimately constrained by what the browser allows, what kind of functionalities are supported by the browser. So for a web attack in particular, the attack has to target HTTP servers on these IoT devices or HTTP-like servers. So how do we find what are these servers? Well, there's a lot of different ways, but for our paper, we did a simple procedure in our laboratory. So we started off by setting up a Raspberry Pi as a Wi-Fi access point, and we connected our about 15 IoT devices and an Android phone. So the reason why we need the Android phone is because many IoT devices interact or are controlled by an Android or a mobile app. So we needed this phone to control and interact with the devices. So then we use this Android phone and these apps to use some of the device functionalities, and we took packet capture at the Raspberry Pi to observe what was happening. And in particular, we're looking for local traffic between the Android app and the IoT device and things that look like HTTP traffic. So here on the, I guess, your right-hand side are the list of 7 IoT devices where we actually found some of these HTTP endpoints, these HTTP servers. So it is actually interesting to note that not all devices do have these exposed services, so not all devices are vulnerable to web-based attacks. So then we augmented our understanding of these 7 devices by kind of looking up for further documentation online on other HTTP endpoints. And in total, we found 35 GET endpoints and 8 POST endpoints. So these are really the HTTP servers that we can potentially target with a web-based attack. So now let me talk about the first attack, which is identifying local devices, local IoT devices on the network. So this might sound like a pretty innocuous thing. Oh, you just found out what are the devices on the network, but I'll talk about some of the implications later on. So for this, let me kind of walk step by step through what this attack might look like. So we have the victim who's loaded a malicious website in the browser, and the attacker starts by getting the local IP address of that host. So it can do this in a variety of ways, but one way is through the WebRTC session description protocol. And now it knows its own IP address. And the reason why it wants to know its IP address is so that it knows what subnet it's on. And it'll become a little bit more obvious in the next step why that's interesting. So let's assume that there's another IoT device on the local network at a different IP address. So here we have a WeMo switch at that particular IP address. The second step is going to be for the attack website to try and find out what are the other active devices on the network. Here, we're not trying to figure out which devices are IoT or not. We're just trying to find which are active devices. So we actually take this kind of approach that has some caveats, and I'll talk about it in a second. But we start by scanning the entire local subnet, which is why we needed to know our IP address originally. And we do this by sending GET requests via the JavaScript's fetch API. And we send this to port 81. And the reason why we do port 81 is because there's usually not a network service actually listening on port 81. So then the attack website will measure the time that it takes for this GET request to finish, and one of 2 things will happen. So in one case, there is a device at the target IP address, so at the scanned IP address, and that means when the JavaScript creates a new fetch request, a new GET request, we'll create a new TCP connection to port 81. So we'll send the TCP SYN packet, but because the WeMo switch does not actually have a service listening on port 81, it'll send a TCP reset to tear down this connection. And this is really quick. It's just one local network round trip time, and then the GET request completes. In the other case where there's not a host at the IP address, then the SYN packet gets sent to essentially a void because there's no actual device there, and there's nothing that's sent back. So in fact, the GET request only completes when the TCP handshake times out, and that's much longer. So by looking at the difference between these 2 scenarios, by looking at the timings, using this timing side channel, you can actually kind of detect whether there's an active host at a particular IP address or not. Now, there are some caveats to this. For example, not all OSs, not all devices necessarily send TCP reset packets when there's not a listening port. And there potentially could be some network service on port 81, but in practice, we find that this works pretty well, and it worked against all of the devices that we targeted. So now the attacker knows, hey, there are these particular active IP addresses. Now we want to figure out which of them are associated with IoT devices and which are not. For that, we're going to now use those HTTP servers, those HTTP endpoints that we found earlier, because many of them are actually unique to particular devices. So if we detect that those particular endpoints and the resources on there that are unique to a device are there, then we can actually identify that device. So to do that, we send GET requests via the HTML5 audio element. So what we do is for a particular HTTP server and a particular resource that's unique to that device, or to a device that we're trying to see, is this, say, a Wemo switch, we'll load it as the source for the audio element. Now, none of these resources are actual audio files, so when the resource is returned, there should be an error because these aren't actual audio files. And a media error is actually thrown, and it contains a particular message that we can actually use to identify what case happened, whether this resource existed or not. And I wanted to mention that this is really actually a new side channel because the same origin policy should actually prevent this. It should prevent you from learning information across origins. Here we're not getting tons of information, but we are getting some information that's leaking between two different origins. So for example, let's say the malicious website is trying to get this setup.xml resource. And let's just say, for example, while this looks pretty simple, let's just say it's unique to the Wemo switch. So if you are in the Chrome browser, when you try and load this audio resource, you'll actually get one of two different error messages depending on whether that resource exists or not. So it's a really long error message, so I'm not going to read it here, but you can see that they're different. And now you can actually tell whether that resource exists or not. And if so, then you can actually identify the Wemo switch. For the Firefox, it's the same story with two different messages. Actually, in this case, the messages are even a little bit more explicit whether the resource exists or not. One quick note is that we actually tested this on Safari and on Edge, which is Microsoft's latest browser, and this attack actually doesn't work for a couple different reasons, but the details are in the paper. So with this attack, the website, the attacker, can figure out what are some of the IoT devices on the network by essentially fingerprinting what resources, what HTTP servers are accessible on those different devices. It might sound pretty innocuous, but what are some of the implications? Well, one thing is through this process of doing this investigation, as I mentioned earlier, this side channel about the media error messages for loading audio elements, this was actually something that was new. It was not actually supposed to be the case because the same origin policy is supposed to prevent this, and we reported it to the browser vendors, and we actually got a nice little Chrome bug bounty for this, kind of just legitimizing that it was actually a concern. Got us all a nice dinner. Now, the more interesting thing is that this attack is really a stepping stone to further attacks because this allows the attacker to be able to focus specifically on the devices that they detect on the network. So this really, by itself, may not do a lot of damage from the attack standpoint, but it can allow for further, more damaging attacks. I think the most concerning thing about this attack is potentially the privacy leaks. In particular, you can now fingerprint a network by seeing what are the devices on that network, and you can potentially profile the user. For example, if the user has certain sensitive devices or certain expensive devices, you may be able to tailor or ads for that particular user or just track that user better. So with that attack, it seemed pretty innocuous, but this one should hopefully be a little clearer what are the damages. So this is an attack that's going to allow us to access some of the data on the IoT devices as well as control many of their actions. So here, we're actually not going to do a new attack at all, but rather we're doing something that's actually really old, and it's an attack called DNS rebinding. This is an attack that actually fully bypasses the same origin policy. Unlike earlier, we had this side channel where we gained a little bit of information. This is an attack that's going to allow us to fully bypass the same origin policy. And it's actually, like I said, a really old attack. It's over 20 years old, and the fact that we can still do it now, especially in the day and age of IoT devices, is pretty concerning. So this attack does require the attacker to have a little bit more capabilities than your typical web attacker. So the typical web attacker has a malicious domain and web server. The one thing else that DNS rebinding attacker needs is control of the authoritative DNS server for that malicious domain. This is really not a significant hurdle, though, for an attacker because many registrars allow you to select a custom name server, and you can just run any name server that you want as long as you just set it with the correct registrar. So let me kind of illustrate how this attack works. It's a little bit more complicated than the previous one. So we start with the case where, again, we're on the local network, and we have an IoT device, and we have the browser. And the attacker has convinced the victim to visit this malicious website. So let's say that the malicious website is attacker.com. So the browser is trying to go to attacker.com, and like with any website, it needs to first go through DNS. So it'll actually query the authoritative name server for attacker.com to figure out, hey, what's the IP address of attacker.com? But in this case, as I was mentioning earlier, the attacker controls this name server, so the attacker can control what the DNS responses are. So the attacker is actually going to respond with the actual server's IP address, but with a very short time to live, a very short TTL. So this is an example of what the the DNS response might look like in such a case. So here, attacker.com gives the real IP address of the server, but with just a 1-second TTL. Now, the browser, with the actual IP address, will contact the web server and load the resource. And this is a malicious web page, so now the browser is running the attacker-controlled domain. Now, the attacker takes the next step, which is to load a resource called test, or it could be any arbitrary test resource, but just some resource. And one of two different things will happen. So let's say that the attacker.com DNS record is still cached. So it's, in that case, the website can, the browser knows already the IP address of the domain, so it can talk directly to the web server and go fetch this test resource. And because we're in the same origin, this is still attacker.com, it can actually look at the response and see that, hey, this is the right resource. This is really coming from my attacker.com web server. Now, in this case, we're not done with the attack because we haven't actually attacked the IoT device, so we'll wait and try again. Now, we'll keep doing this until the DNS record for attacker.com is actually flushed from the cache. In that case, we have to go through DNS again, so we're going to contact the authoritative name server yet again, and this is under the control of the attacker. So the attacker will actually respond with something different now. It'll actually respond with the IP address of a local target, which is the Wemo switch, which is the IoT device that you want to potentially attack. And now it can use a large TTL so that this doesn't get expired from the cache soon. Then when the attack website tries to load the resource test, it's going to go to the IoT device, not the original web server. This is because attack.com has actually now been rebound to a different IP address. It used to be the original IP address of the actual server, but now it's actually this internal IP address. That means that the malicious website can now start sending arbitrary requests to attacker.com and actually access these resources, but they're all going to the IoT device rather than the original server. So what can we potentially do with this? I'm going to just kind of give you a flavor of some of the attacks that can be done, but the paper is much more detailed about what are the conditions in which this attack can be successfully pulled off and kind of what are the damages. So just as kind of an illustration, I'm going to use the Google Home and the Google Chromecast. So one of the potential attacks that can be done is to just play arbitrary videos on the Chromecast. And you might wonder, okay, so what? You're playing some videos. Why is that interesting? Well, one thing this can be used for is for view fraud. So you may have heard of this when you have like a video streaming service that shows, the number of views. This is often heavily influential for what videos are displayed to users. So if an attacker can pull this off at a large scale, they can inflate the views for a particular user and potentially monetize, say, for the ad revenue. We've also heard lately about some attacks using voice commands against IoT devices, such as home assistants. So if you are able to play a video, you might actually be able to play a video that has a sound that triggers certain actions for these voice-controlled IoT devices. You may have heard about the Super Bowl ad that triggered like Amazon Alexas in homes. So imagine something similar, except perhaps a little bit more malicious. Another attack that you could potentially do is just reboot the devices. This takes about 30 seconds for each of them to reboot, so you can, kind of do a somewhat denial of service attack. And then a final case that I'm just going to talk about, and there's many more in the paper, is that you can actually scan for, you can actually tell both the Google Home and the Chromecast to scan for local Wi-Fi networks and return the SSIDs and the signal strengths. Now, this information may seem kind of meaningless, but it turns out that you can actually use this to do pretty precise geolocation at a much finer granularity than IP geolocation. So, so I have a little demo of these each attacks. I should take about 1 minute for the demo, so hopefully. Yeah, so this is going to show the first attack where we're going to play just an arbitrary video. The attack takes about 8 seconds. You actually may have heard about DNS rebindings in the news lately. A lot of those attacks actually took a lot longer. This was just nothing fundamentally different, but just engineered a little quicker. So here we got the Chromecast to, which is in the upper right-hand corner, to play the Rickrolled video. And this is all being done just by the web page. So in the second case, we're going to just reboot the Chromecast. And if you reboot it over and over again, sometimes you can actually get it into kind of an unstable state or a state where you might have to factory reset. So you might be able to do a kind of denial of service sort of attack there. So here, after about 8 seconds, again, we get the Chromecast to actually reboot. And then I think the final example is the one I like the most, which is using this Wi-Fi network to actually do geolocation. So here we're attacking the Google Home, and we're going to find the Wi-Fi networks that the Google Home is nearby and connected to, and then we're going to feed it to an online service that takes this Wi-Fi information and does geolocation. So we actually did this test while we were at Princeton Center for Information Technology and Policy, and I don't know if you can read it, but as you zoom in on Google Maps, you actually see that it's the exact same building that we tested in. So this is a much finer granularity than, say, IP granularity, which would tell us that, hey, we're probably just in Princeton. This actually tells us literally the address that we're on. All right. Can I get the next slide? All right, so just quickly, I think the implications of this are probably pretty obvious. You can control a lot of these devices, and in some cases, if some of the servers have vulnerabilities, you potentially can exploit them for full compromise. This is also a massive privacy leak because you can really access some pretty sensitive data on some of these devices, such as that geolocation. So kind of just in conclusion, here I've kind of tried to demonstrate that the barrier to attacking some of these devices, even if they're behind a NAT, is really low. It's lower than malware. All you have to do is get someone to visit a malicious website. And this makes it, this highlights a need for us to really consider defenses against lateral attacks on IoT devices, whether it's from malware or local infected devices or just web browsers. So with that, thank you very much, and I'm happy to take any questions. Yeah, so with the first attack, I was saying like you scan the local network. You can actually do this in parallel. Browsers do limit the number of requests that you can usually send, but they also provide these things called web workers, which are essentially separate threads, so you can actually just parallelize the scan. So that attack actually you can do really quickly. With the second attack, it takes a little time because you need to wait for the DNS cache to time out, and that's really the bottleneck there. And unfortunately, as the web attacker, you don't really get to control that part. So it depends on how quickly that happens. And in the paper, we actually talk about how this varies across different operating systems. But 8 seconds is usually fairly quick for, sure, if someone just opens a malicious website and immediately closes, maybe you can't pull it off. But in many cases, you might be able to get the user staying on your website for long enough to pull off the attack. Yep. Sure. Yes.
The parallel to this would be in corporate network, for instance, Google, companies like Akamai, for instance, now treat every request as coming from an attacker. So even if you're within the corporate network, the authenticator. Do you think there's a parallel here?
Yeah. So just to repeat, that's the great observation was that it seems that these IoT devices are just assuming everyone on the local network is safe. And that's certainly the case. And arguably, this is the case not just in IoT, but in general, we often think of the local network as the more safe domain. So in the paper, one thing I didn't talk about here for lack of time was some of the potential mitigations against these attacks, and indeed ways where the devices don't necessarily trust the requests or do further validations of the requests they receive could help mitigate some of these problems. Yep, great, thank you.
Thank you. Yeah, so this is Chuhan, and the talk is about detecting IoT device outside the net. And first, why do we care about IoT device, right? So it's mentioned multiple times today, and they cause DDoS attack and other attack very badly. Like a slight recap is, say, in 2016, 60 to 20 gigabits attack against Crib on security.com, and 1 terabits against OVH, and the more famous one, or infamous one, 1 terabits per second attack against Doan. So this one is lasts about 5 hours and affect a lot of services. I list them there, and it's not visible, but there are a lot of them. And there's some bigger names like Amazon.com, Twitter.com. So if you watch the news, like Twitter is down, say for a morning. And so conclusion is vulnerable IoT broke the internet. And so that inspired us to do this work. Want to detect IoT because they threaten the security of the internet ecosystem. So as a first step, like first baby step to understand this threat, we want to know the location, distribution, and growth of IoT device by finding those devices. And we believe, like, with the method and knowledge we provide, we can do a couple of things. So we can know the scale of the IoT security problem, like where are the devices, how many are them, and we can also know the problem's growth, like how fast is the IoT growing and the distribution, where they are. And so contribution is we have a method and we apply it. So 3 parts of this talk. We'll start with the method, then we'll go into the results, and we'll go into future work. And so our detection insight is simple. So we observe IoT device, they mostly talk to servers. So IoT devices do multiple things, right? Some use STAN to do net transversal, and some they do port mapping, but we want to find a single thing that almost all of them do. They talk to server. And so if we know those servers, we can identify IoT device. And since we find server combination are quite unique, so we can also categorize the type of device. And the other huge factor we choose this signal is it's robust to NAT, right? We have considered like fancier stuff like the rate they talk, the timing they talk, do they sleep in the night, and do they like send certain amount of packet? But none of those work outside the NAT, right? Because when NAT mix the traffic together, like all those signals just adds up, and you just can't like distinguish device from device because they are all messed up. So, but a nice thing about packet exchanges is even if it's mixed, it still works. Say, IoT1 talk to server A and B, IoT2 talk to server C and D, you still say server A, B, C, D outside the NAT, right? And in this simple scenario, you know, those 2 guys are probably behind the NAT. So the method really boiled down to only 2 steps. First is determining server you want to look for, then look for those server. And so, but to determine those server, we want to do a couple more filtering that just use whatever server we found to increase the accuracy of detection. So we first found a superset of all the server that sample IoT devices talk to. And we use 2 group server, one group device we own, the other device from traffic measurement shared by UNSW, you guys. And so a typical query look like the one I showed there. So that particular one is from like a Philips light bulb. You visit a website called ecdinterface.philips.com. So we got all the server, and that's the candidate. Then we filter them, right? Because we want to increase the detection accuracy. So we filter out two sets of server. First one we call third-party server that are not owned by IoT manufacturer. We find them mostly provide public service like time service, NTP. Almost every device talks to some kind of NTP server. And they also include like video streaming, the news website, and that kind of stuff. So the thing about those servers is they talk to a wide variety of devices. So there's no uniqueness about who is talking to them. So it causes confusion in detection. The other set we call human-facing server, and we define it as a server who also talks to human, maybe a laptop or cell phone. And the test we use is for the third-party one, we find server domain that contain no manufacturing information. Of course, there are more like subtlety about those. And for the bottom one, we use a server respond HTTPS request with content. So about this test, it's not perfect. You find out a subset of human-facing server who provide the website, right? But so there are certain disadvantage of using that, but that's the best we can do, and that's what we're doing. And we also, so we use the rest of the server, which we call device server, because they're owned by manufacturer and the served device only, hopefully. And we only use them for detection. We also handle the case where servers are shared by devices. So if two devices talk exactly the same servers, we treat them as the same because they look the same to us. If different devices share partially the server, then in some cases they're distinguishable, and in some cases they are not. And also considering the fact that we don't necessarily observe all the server device visits, so we probably have a partial knowledge of the server. So consider all the complex cases, we choose to go conservative. So if we detect device who share some server, then we detect at least one of them, instead of saying definitely we detect both of them or one of them. We also need to track server IP because we find server by domain name. We measure device, the DNS query from devices, so we get a domain name. But when we detect server in the wild, we use IP address. So we need to keep track of the server IP change, server IP of the server, and we all know that IP can change over time, and they may be different over different geolocation. So as a conservative measure, we track IP roughly in the same time and from the same location and the network traces. And we apply this, oops. And the next step is to look for those server in traffic. So now we basically have a list of server, a list of filter server for each device. And we want to define a threshold that we want to use. So it's a majority, but not all the server. The reason we want to set a threshold is, one is because we think the test we use for human-facing server is not perfect. And we also want to take consideration of the fact that we may have short measurement in detection, or we may miss server, and so all kinds of cases. We want to tolerate that. So we have a majority, and there are more subtlety about the threshold. It's in the paper. We basically interpret traffic to this number of server from given IP to presence of that devices. And we apply this to two sets of internet measurement. We use 29 type of ID devices in our detection. 10 we own, 16 from UNSW, and we extract 99 device server using the filtering rule from those 26 devices. So first we apply it to the traffic we capture from USC campus gets Wi-Fi. So we basically did a 6-day measurement, and we drop payload and anonymize IP to hide the privacy information. And we use the 99 server and 26 devices we got. So we basically have certified detection from a user IP, and those two stands for at least one level 2 device. It's introduced by the conservative measure we described earlier. And first observation is IP-based devices tend to have multiple devices. So that suggests they may be behind on that. And we also find one user we find 3 IP with the same devices, which look awfully like a user whose IP changed 3 times during our measurement, but we can't confirm because we don't have access to raw capture and DHCP data due to our agreement with the university. And so I think the takeaway from this data set is it shows the approach works in a campus. And we also like to point out it's a huge underestimation of deployment on USC Wi-Fi, on USC campus, because guest Wi-Fi is only a small fraction of the campus traffic. And we also apply it to IXP to find IoT device in the IXP customer. And the data sets we use are FRGP, flow level traffic from this IXP called FRGP. The measurement is, it's from 2015. And so the problem is we don't have our server IP back to 2015, so we end up using a commercial passive historic DNS data from Farsight Security. And we find safety detection of only two types of IoT device, which is, it looks too small for IXP, right? And we believe the incomplete service IP causes under detection. So there are many reasons. We have more discussion in the paper, but the higher bit is the Farsight data only cover IP for 51 of our 99 server, and even for the covered server name, the data potentially miss IP because we find the server name we have, many of them are rotating IP within a pool because the Farsight data, they are doing the passive measurement, so they don't necessarily observe the whole pool. And so we try to redo this detection with maybe more complete set of server. And this time we only apply to half a day's data because we don't have enough time before the deadline. And we use IP we collect in 2017. So to ensure this thing work, we verify the IP for our server. They are either stable or they are from stable pool. They're rotating within a very stable pool. So, and we find at least 4 more type of device only using half a day's data. So the conclusion is it's hard to detect IoT device with this method in the past because server IP change, even the commercial DNS data has very limited coverage for this usage. And future work, I think there are 2 main drawbacks of this method. First is you require you know the IP, so you can't apply this to old data very easily. The second one is the server name you measure are almost always incomplete. So it's better if there's a way you can just learn the server during your detection. So those are two for our future work. So conclusion is we develop a detection method based on IP, and we apply it to data and found a bunch of devices. And so please check our paper. We have a validation of how accurate this thing works. And we also have a tech report where we implement the future work I just mentioned. So we have a DNS-based method. You can just apply it to the old data, and you also can learn new server during detection. I also have a third method. So it's in the tech report, it's in the URL. So please check it out. Mm-hmm. Mm, yeah, I think it's pretty fast because if you know the list of IP you're looking at, right? You throw into that hash map, searching is like 01, right? So it's pretty fast. And then you just kind of go through the list of device and server mapping to find which one is present. It's pretty. Mm-hmm. Yeah. So what we find is, I think we observed this thing for half a year or slightly more than that. So we probably do this. I can give you the more accurate description. We probably do it like about 1 year or even more, 2 year. We find the server name barely change. We track for like 26 devices, and we find only one name change, and it's just a CNAME kind of change. So essentially, it's the same server name, but IP definitely changed. But I think like if the server name doesn't change, you don't have to do the whole filtering process again. Yeah. Yep. Mm-hmm. Mm-hmm. You mean the server name? Yeah, many of them are on Amazon. Yeah, yeah, yeah. I think what we. Mhm. I think, yeah, that's definitely the trickier part of this method. What we do is we try to track the IP ourselves and try to stay close to where the network traces is, and we keep all the different IP we see. And we, mhm.
Yeah, in other words, does your method work because of the accuracy? As you talked about the easy to address issues in sampling, will it be effective if the data set is heavily sampled,
Mhm.
as in the case of an IXP? And where exactly do you envision this method applying?
Yeah, I think this will work for, I think, so if yeah, I think the accuracy, so of course you can have very large aggregation, like more devices share one IP, but I think like what we know is like the home level, so you have 10, 15 device, it works fine. But say you have 200 devices behind one IP, then you may not work that well because everything just cramped together, right? Does that address your concern? We can talk offline. Thank you.
Last speaker of this session is Dinesha. She is an undergraduate student at Princeton University. She works with as an introducer. She's about to enter her fourth and final year. And her research interests are in IoT privacy and using machine learning for social good. And what's nice about this paper is it uses a very simple but clever technique to secure users in a home environment. And let's see how it works.
All right, hi, I'm Trisha Dada, and today I'm going to be talking about a developer-friendly library for smart home IoT privacy-preserving traffic obfuscation. I worked on this with Professor Nick Feemster and Noah Apthorpe at the Center for Information Technology Policy at Princeton. Okay, so the motivation for this work, like the motivation for all of the projects in this workshop, is the recent proliferation of IoT devices. And even though these devices have the potential to really revolutionize the way that we live, they also come with a whole host of security and privacy concerns. And the one that I was looking at in my work is this idea that if you have traffic from an IoT device, even if that traffic is encrypted, you can tell when the device is being used. So if you look at that graph there, it's a little hard to see. But if I ask you to look at it and tell me when that device was being used, it would be pretty easy, right? You just look for the peaks, and that's when the device is being used. The problem with IoT devices is that they're really specialized. So when a device is being used, it can tell you something about what the user is actually doing. So for example, this is traffic from a sleep monitor. And when a user is using a sleep monitor, it either means that they've gone to sleep or woken up. So if you can tell that they're using it, you can tell something about their actual human behavior beyond just that they're using the device. And so my goal was to create a customizable library that could prevent this kind of inference from happening. And I want to emphasize that one of our key goals in this was to make it flexible for a variety of different kinds of devices. So first, I want to go a little bit over the threat model that we were working under. So we assume that the attacker has access to encrypted traffic from IoT devices. This can be someone like a Wi-Fi eavesdropper or WAN eavesdropper. And we assume that they are trying to infer user activities. They're trying to figure out when users are using the devices and then what they might be doing beyond that. And some people who might have access to this kind of information are ISPs, internet service providers, or perhaps if an attacker is able to get a malicious device into your home network, or even your neighbor could potentially eavesdrop on your Wi-Fi network. So in terms of related work, the two colleagues who I worked with did implement a simple solution to address this concern. What they did is implement a traffic shaping solution on a router. So you can look at that graph there. Basically what they did is they enforced a constant rate of traffic leaving the router. So those peaks that you see in the original traffic are no longer there in the shaped traffic. Now this does preserve privacy because the attacker can't really infer anything from the traffic that they're seeing, but there are a couple problems with it. So the first is it has very limited flexibility. It just shapes the traffic at the router, and it doesn't really consider the particular characteristics of devices. It also can impose fairly long delays. So they tested it with an Amazon Echo, and you could wait several seconds for a delay, which kind of impacts user usability. And the other problem is that because this is at the router level, it doesn't prevent against certain cases. So for example, if there is a device on the same Wi-Fi network that is trying to sniff traffic, this would not protect against that because it's implemented at the router level. Okay, so before I go into how the library actually works, I want to go over a few conceptual concepts. And the first is traffic shaping. So because we're assuming that traffic is encrypted, the attacker has access to basically two pieces of information. The first is the size of the packets that are being sent out, and the second is the time between them, which I might call interpacket delay. And so these are the two variables that we have to play around with in our traffic shaping. And there are three main ways that we do this traffic shaping. They're quite simple. The first is padding, so we can make a payload look larger than it is. The second is fragmentation, so we can make a payload look smaller than it is. And the third is cover traffic, which basically means we're sending traffic that has no relation to the functionality of the device, but to the attacker, it looks just like normal traffic, again, because this traffic is encrypted. And just a side consideration, because we are doing all this manipulation, we implemented a very simple recovery protocol that allows us to differentiate between real and cover traffic and reassemble padded and fragmented traffic. Okay, so as I mentioned, one of the main goals in this work was to try to make a library that could be customizable for a variety of different kinds of devices. And one of the ways that we did that was divide devices into different categories and then create solutions for each of these categories. So as I mentioned before, one of the problems with the router solution was that it didn't really take into consideration the particular functionality of the device. So we've kind of divided devices into two categories, high latency and low latency. And basically, high latency devices are devices whose functionality would be impacted by very long delays. Or sorry, would not be impacted by very long delays. So for example, the sleep monitor, if the server finds out that you went to sleep 9 seconds after you went to sleep instead of less than a second, it's not really going to impact the functionality of the sleep monitor. Conversely, if your Amazon Echo takes 9 seconds to respond instead of less than a second, that's going to affect user experience. And so we want to treat these two cases differently. So that's high latency devices and low latency devices. In the category of low latency devices, we split devices further into two categories, low bandwidth low latency devices and high bandwidth low latency devices. And that's basically exactly what it sounds like. High bandwidth low latency devices use a lot of bandwidth during user events, and low bandwidth low latency devices do not use as much bandwidth. Again, these are all very relative definitions, and we haven't defined any hard boundaries, so we imagine that developers may have to experiment a bit to figure out which solution works best for their device. So for our work, we decided to focus on high latency devices and low bandwidth low latency devices. One of the reasons is that these two categories cover a wide range of devices. They cover sensors, sleep monitors, things like light switches. So we are addressing a whole bunch of devices. And also these particular devices, their traffic is more amenable to shaping. So the high latency devices can tolerate very long delays, and the low latency devices don't send out that much traffic, so masking what they send out, it won't take up that much extra bandwidth. Conversely, high bandwidth low latency devices are kind of hard to deal with, so we decided to put that outside of the scope for this work. So how did we, as I mentioned before, the reason that we created these categories was so that we could create different solutions for each of the categories to provide flexibility for developers. And so for high latency devices, again, because they can tolerate very long delays, what we can do is just impose arbitrary distributions of payload sizes and interpacket delays. And how that works is basically we can choose a payload size, we can choose an interpacket delay, and then we can send out that information. And if there's real traffic to be sent, we can send out the real traffic, and if there's no real traffic that needs to be sent, we can just send out cover traffic. And again, because the distribution of payload sizes and interpacket delays that an attacker is seeing are completely independent of what the device actually needs to send, this is completely secure. For low bandwidth, low latency devices, again, low latency devices do not tolerate long delays very well. So basically, as soon as they need to send traffic, we have to send it. And so how we kind of shape their traffic is basically enforcing a constant rate of traffic. That's a little bit higher than their peak rate. And we basically just do this with a constant interpacket delay and a constant packet size. And again, because these things are constant, an attacker can't infer any information from the shaped traffic. Okay, so how did we actually put these ideas into a library? The library is very simple. It just replaces normal send and receive functions with my send and receive functions. And this is a diagram of how that works. So on one end, you have the sending end, which is the device, and it will call my send message function. Now, the send message function is initialized with inputs from the developer, and we imagine that these will help developers to customize the solution to their particular devices. They essentially just specify the parameters for the distributions of payload sizes and interpacket delays. And so once that send message figures out what size packet to send and when to send it, it will send that out, and that padded or fragmented or covered traffic is what the attacker will actually see. So again, it doesn't correspond to what was originally trying to be sent. And then on the other hand, we have the receive message, which basically undoes all of the padding and fragmentation and discards any cover traffic and passes that original traffic back up to the receiving end. So the receiving end only sees what the sending end originally meant to send. Okay, so in terms of evaluating the effectiveness of this library, what we did is we simulated the functioning of IoT devices on computers. So how that worked is used Wireshark to record PCAPs from a variety of IoT devices, and then we used two computers. One had the server-side code running on it, one had the sending code on it, and basically the the laptop that was imitating the device would basically send packets of an appropriate size with the appropriate delay, and then we could use Wireshark to capture the traffic that was actually sent out by the library. Okay, so this is an example of how the library works for high latency devices. Again, these are devices that can tolerate very long delays. And so this, as you can see in the first graph, we see peaks that clearly correspond to activity. And then in the second graph, those peaks are no longer there. And I want to reiterate that we can safely say that the peaks that do appear in the second graph have no correlation with the peaks that appear in the first graph because, again, we are drawing the packet sizes and the interpacket delays from arbitrary distributions. And so I should have mentioned this before, but we want to evaluate our solutions on two things. The first is how well privacy is preserved, and the second is overhead bandwidth consumption, because if this uses too much bandwidth, then it's not viable. And this particular solution with these particular parameters used around 1.5 kilobytes per second of overhead bandwidth. And this is an example of how the library works for low bandwidth, low latency devices. So again, for these devices, we're enforcing a constant rate of traffic that's a bit higher than the peak rate of traffic. And you can see here that it's a little jittery because of jitters in the network. But the shape traffic is constant, and so you can no longer infer when the user was actually using this device. And so it preserves privacy, and these particular parameters use around 4 kilobytes per second of overhead bandwidth. In addition to looking at particular devices, we also looked at how playing around with parameters affected how much bandwidth was used. What we found was pretty much what you would expect. If you increase the average payload size, the amount of bandwidth goes up. If you increase the average delay, the amount of overhead bandwidth goes down. And to put the numbers that I kind of threw up about bandwidth consumption, so if we're using 4 kilobytes of overhead bandwidth per second, that's around 10 gigabytes of overhead bandwidth per month. And Comcast and Cox, which are two of the biggest ISPs in the US, they impose 1 terabyte data caps of 1 terabyte per month on households. And so this would only be about 1% of that per device. So that seems pretty reasonable. Okay, so in conclusion, IoT devices, as we know, can leak a lot of information about their users. We're particularly concerned with attackers being able to infer activity about users in their own home, even when traffic is encrypted. And to combat this, we created a library that can shape traffic, and we created categories of devices and then specific solutions for those categories. And this allows this solution is a lot more transparent than the router-based solution that I mentioned earlier. It's a lot more flexible, and it protects against attacks where the attacker may be on the same Wi-Fi network. Thank you. Questions? Yeah, the idea is that IoT device developers could use the library. Yeah. Yeah, so in terms of how much power it takes to compute, it's just drawing from random distributions, so it shouldn't be too much extra power. And sorry, what was the last part? I think it's pretty usable, personally. We tried to make you can actually look in the paper for a more specific breakdown of the actual function calls. We tried to make it as similar to Python's function calls as possible, so that should be pretty usable, we think. Yeah. What kind of negotiation mechanism? Right. I assume so. There's a way to standardize it. Right now, we're just using a protocol that is like very simple to reconstruct. The messages. It basically just has whether it's real traffic and like whether there's more messages in the traffic. So it would be fairly easy to standardize that. It would just require more computation on other people's ends. Yeah. So future work would probably be the first bullet is making the solution more specialized for each kind of device, and I think that would hopefully drop the bandwidth cost a bit. In terms of how to actually do that, we did experiment a little bit with trying to create fake user events, so the attacker wouldn't be able to tell which was a real user event, which was a fake user event. We had very limited success with that, but it didn't try it too hard, so definitely could be one option. And then also other future work would be looking into that last category that we decided was out of scope. Yeah, so as it stands now, I kind of monitor offline and the developer hard codes it, but I guess like in the future that I think that would kind of go with that first bullet, try to have some kind of way for us to learn behavior and adapt accordingly. Yeah, it's obscured. Yeah. Yes.
One of the things that you mentioned, which was very interesting to me, was you said that the ideal first root scan analysis in encrypted traffic is ISPs.
I mentioned that they had access to this data, not that they were trying to do this attack. Yes.
But I still have a question.
Yeah.
How do you assume, is it fair to assume that the ISP already is able to detect an individual IoT device's patterns from the patterns of data that it has?
I mean, yes, but if all devices were using this library, that wouldn't be the case.
No, without in the case where they're not using
Yes.
your library, right?
Yes.
Still telling me that it's possible for an ISP that looks at petabytes of data, traffic data, to individually isolate one single device. I'm just asking if that assumption is fair.
I mean, I believe they have the capability to, I think. Yeah.
So I think you'd gain more as more devices use it, right? Like you gain more benefits.
I'm not sure if that's true, because I don't think that's necessary. Maybe it might, for developers, I mean, it's not high cost to use this library, but it might, like, if all of their devices are using it, it might make, like, it might be easier to implement that server code if they have all devices on it, but I don't think it's necessarily a huge scaling benefit.
That doesn't quite what I asked, but we can take
Okay,
this.
yeah.
Any other questions? Boss is eager enough, so let's start with her one more time. So I think we have a break until 3:45. Yeah. So you have
right is forward, left is back, and the right is the laser, yeah.
All right. Everyone, let's get started with the keynote, if you guys can pay attention. So we have an interesting keynote here on DDoS protection using some of the latest advancements in the Linux kernel world. The speaker is Hoping. Hoping Zhao is on the traffic team at Facebook. His interests range from caching, network performance, and security. He graduated from CMU, and before that, he was at Oracle, I think. So let's listen to the DDoS protection talk.
Hi, I'm Huapen. I'm currently a software engineer at the traffic team at Facebook. So the traffic team basically works on layer 4 to layer 7 networking problems at Facebook, and we're kind of the gateway to Facebook services. As for the talk itself, I'm going to talk about Droplet, which is our DDoS protection framework built upon eBPF and XDP. Unlike the previous DDoS, the Keynote, this is going to focus more on the details and how we build it from scratch. So feel free to interrupt and ask questions. I want to make this more informal. So a short agenda first. So I'm going to give a brief introduction to eBPF. Yeah, sure. I'm going to give a brief introduction to eBPF and XDP. Next topic will be Droplet, the DDoS protection framework itself. And I will also talk about the operation lessons that we learned from the last couple years. Last one is about the next steps, what we're going to bring Droplet to. So BPF, what is BPF? BPF is a Berkeley packet filter that is developed by Steve Mencken and Wan Jacobson for the BSD system in 1992. It was introduced or ported to Linux in 1997. The system is kind of like an in-kernel virtual machine with a very simple instruction set architecture. It's one accumulator, one index register, and a pretty simple scratch memory storage. It supports arithmetic operations, logical operations, and forward jumps. Note there's no backward jump here, so you cannot really do for loop. And over time, a lot of enhancements have been made to the BPF system, especially for Linux. There is a just-in-time compilation introduced in 2011, which translates the BPF instructions into native instructions, like x86. So what is eBPF? eBPF stands for Extended BPF, and it's essentially a brainchild of LXC. He's currently a kernel engineer at Facebook, and it's unlike a conventional BPF, eBPF maps to real CPU instructions. It's essentially 10% of the conventional BPF. 60% of x86, 25% ARM, plus 5% RISC. And it supports backward jumps, but with a very limited scope. So you can have like a loop for 20 times or something like that. So what's more important is eBPF provides what is called eBPF maps, which are essentially global persistent data storage that you can use to build, let's say, for networking, build a whitelist or a blacklist or IP addresses or CIDR prefixes. You can also store aggregated statistics, let's say how many packets have been dropped in the eBPF maps. And in addition to the eBPF maps, there are also other Linux kernel infrastructure built around eBPF. For example, you have the kernel verifier to verify your eBPF program to make sure it doesn't do anything crazy. And there's also the JIT engine, which can translate the eBPF instructions to native x86 code. And also a few helper functions which can, let's say, adjust the packet by appending to the header or appending to the tail. So
the use cases of eBPF are essentially two major use cases. I would say networking, which we're going to talk about it today, and also it used extensively in tracing to collect system performance, to debug performance issues on Linux systems. It also can be used for some internal optimization, hardware modeling, and there are even more use cases. So that's pretty much about eBPF, but what is XDP? XDP is built upon eBPF. It's the express data path which runs the Linux kernel. So it's intended to be a high performance network data bus, and it operates at the lowest level of the kernel networking stack, which means it's actually inside the device driver functions. So if you look at the source code of Madnox or Intel card driver functions, there are a lot of XDP routines over there. So it's before when the kernel allocates the sorted buffer, so it has minimal performance overhead. So the nice thing about XDP is that it's programmable at runtime thanks to the eBPF program. So which essentially means you can run user-defined sandbox bytecode in the kernel. So XDP, when people talk about XDP, they usually compare it with the kernel bypass, DPDK, but they're kind of different. Let's take a look at an example of the layer 4 load balancer. So for kernel bypass, you have your fault implying the application logic in the user space. It talks to the device driver to get the packet and decide to forward the packet to the kernel. But with XDP, the XDP program actually resides inside the kernel, and it talks directly to the driver. So the generic packet processor architecture for XDP looks like this. So let's say you have your control logic in your application, in your user space, and the control logic is responsible for load and configure the eBPF programs. And you hook your eBPF programs into the kernel hook point, and it gets packet. The packet is passed to the eBPF program. It does some parsing and processing. There are different actions you can take in the eBPF program. For example, you can decide to drop the packet while XDP drop, or you can forward the packet to the device so it goes to another host. Or you can decide to receive this packet locally after generic receive overloading, and after some like a packet steering technique, for example, RPS or RFS, the packet is passed to the regular TCP IP stack, and then eventually it goes to the application space. So that's pretty much about the primer. So next topic is going to be droplets, how we built the droplet from scratch. So I think most of you have seen this graph. Again, the dying cyber attack occurred in 2016. Dying is a DNS provider for Twitter, for Spotify. Due to this attack, a lot of people cannot post their status on Twitter, cannot listen to their favorite music. It caused a major outage of internet, especially for the US Eastern region. So at Facebook scale, we also saw a lot of DDoS attacks against us. So here in this graph, I'm showing two attacks which happens in a 2 minutes timing window. The first one, the red one, which is a reset flood, and the second one is a SYM flood. So when the attack happened, the number of the PPS, the packet per second that we process on our edge network was orders of magnitude higher than what we process normally. So some like anti-DDoS history at Facebook. Before we invented our own in-house solution, for the detection, we use a third-party solution, but there are multiple issues with the third-party solution. The first one is it took like more than 5 minutes to detect And it has poor scalability given the scale of the Facebook. And there's essentially no integration with Facebook internal tools, which are quite powerful to analyze traffic. And for the mitigation, it was quite a manual process to come up with edge echoes and push these echoes to the routers. But now this has changed. So for the detection, we have an in-house solution which can detect the attack within seconds. And for the mitigation, which is what we're going to talk about, which is the droplet framework. So in addition to droplet, when we think about how to defend against DDoS, we take multiple approaches. The first one is to harden and scale our edge network. This either means to increase the performance of one host. That's to do optimizations of your applications so they run faster. And we also add more hosts to our edge network. The second point is about to scale up our layer 4 load balancer, which is what we call shift. So we rewrite the forwarding plane entirely in XCP, and we saw a 10x performance improvement over the previous approach with IPOS under DDoS scenarios. So the last one is to develop a flexible mitigation countermeasure framework, which is Droplet itself. Droplet is kind of a host as solution, and it works in concert with our layer 4 load balancer software. So how does these two work together? This is essentially how the traffic is processed at the Facebook Edge network. So in the first place, we use ACM to route the packet to a certain layer 4 load balancer, and that's droplet plus shape on the graph. And the packet first passes droplet check to see whether it's a legitimate traffic or whether it's a kind of a DOS attack. And if we decide it's legitimate traffic, the packet will be passed to Shiv, and Shiv use a 5-element tuple to constantly hash the packet to a layer 7 load balancer backend, which is processing in this case. So essentially, Droplet and Shiv runs on the same machine. That's a commodity Linux hardware server. So when we first started this project, we had several design requirements in mind. The first one is we want super fast packet drop. So we had a 40G network card at our edge network, and we want to drop at that line rate. And we also want to drop at the earliest stage in the networking stack, which means we don't want to waste processing power to process this packet and later figure out the packet is some garbage. We also want programmability, which means it must be very easy to develop and very quick to deploy these DDoS countermeasures. We definitely don't want kernel reboots because that takes minutes or even hours. So the last one is about flexibility, which means we want to quickly activate or deactivate certain mitigations. So it turns out that all these requirements can be realized by XCP drop, and it can even drop at a hardware limited rate. So how it looks like with the droplet. So in the first place, we have the eBPF programs written in C. These eBPF programs are predefined countermeasures. So we ship these eBPF programs as configuration files for the droplet service itself. And then we do runtime compilation of this C source code, which translates this C source code into eBPF instructions. And then the droplet service takes care of the eBPF map setup, which could be, let's say, blacklist our IP addresses, and hook these eBPF instructions into the Linux kernel. So lastly, when the packet arrives, it will invoke the XDP code path and starts running. So this is actually the first version of what we had in production. So the mitigations are expressed in the restricted C syntax. So let's say if the source IP address is in the blacklist of IP address, we just drop the packet. Otherwise, we pipe this packet to the next filter in the chain. So the runtime compilation is achieved with the BCC library. It's an open source library from the IOWiser project, which try to which has a lot of utility scripts and functions to help you to use eBPF. And the eBPF maps, which can contain the list of IP addresses or list of ports, are filled from user space with live data, which means, let's say, once the map is updated within seconds, the map in the kernel space will be updated as well. So the C source code was disliked by the network ops people at first because, I mean, it has pros and cons. It's pretty easy to develop a C source code, a C file, but it has steep learning curve because it's a restricted syntax. It's not the standard C, and it's error prone when you're not familiar with this syntax. So what we decided to do is to reuse the PCAP expressions because it's pretty easy to integrate with our existing toolchain, and also every network operator is familiar with the PCAP expression. But how do we convert the PCAP expressions into eBPF code? So we first thought about using libpcap, but libpcap only generates BPF instructions in the C BPF ISA. And it's over the years, a lot of features have been added to the libpcap library, and it's very hard to extend the syntax for feasible use cases. And the optimizations applied in the libpcap are handcrafted, and we don't get a performant code. So we decided to write a custom PCAP compiler in the end, and the compiler front end is written in C++, and the front end translates the PCAP expressions into LLVM intermediate representation. The LLVM is a compilation library, and the IR here is just you can think of it as assembly code for LLVM. So then this LLVM IR is optimized with a lot of LLVM passes, for example, the constant propagation or the standard compilation technique. And for the backend, we use the LLVM OCJIT, which is the on-request compilation JIT framework, to convert this IR into eBPF code. So let's take a look at the simple example here. This says this filters the TCP packet with destination port 443, and also with the same flag set. So we constructed the abstract syntax tree of this expression in this, like this. On the top level, you have the logical AND of two sub-expressions. On the left-hand side, you have the TCP destination port is equal to the immediate number 443. And on the right-hand side, you have the TCP flags field, and with the TCP SYN flag. So the result of this binary AND is not equal to 0. That's how we constructed the AST in the compiler front end. As for the code generation, let's look at this. Let's look at this right-hand side only. So let's say we first have this line 53. We load one element pointer from the transport header with 8-bit weights, and then we get the pointer to the offset 13 with a size of 1. We compare the resulting pointer, which is the point of the TCP flex field, to see whether it reached the end of the packet, to see whether this packet is valid or not. If it's valid, we then load this field, load this 1 byte from this packet offset and say, do some like arithmetic operations, and finally binary end with the immediate number 2, which is a TCP send flag, and compare the result to see whether it's 0. So this is non-optimized code, so you can still read it in some way. So that's what we do about the two types of mitigations: the C source code and the PCAP expression. But one additional feature requirement came up during the development was that we wanted to retain the attack data. But the attack data is actually dropped in the kernel space, but how can we dump that to the user space? So it turns out that eBPF provides a helper function called BPF perf event output. You can dump any certain kind of metadata into using this function to a queue. And from the user space, you can pause this queue with perf event open, and you can read the events from this queue. This way, we can get, let's say, the first 64 bytes or first 128 bytes of the packet. So we support 2 packet sampling modes. The first one is random sampling. We just use get serial number and compare that with the threshold to see whether this packet should be sampled or not. We also support consistent sampling using the 5-element tuple, but this can be configured on a per use case basis. So the packet metadata is dumped to like an outline pipeline, and we do extensive analysis of this packet metadata to see whether there are any false positives, any signature we miss. So here comes the testing part. So we have these powerful C programs and PCAP expressions, but how can we make sure they're actually dropping the correct packets? In the first place, we don't want to test in production because that's too scary. So what if you make a simple mistake and drop all the incoming SIM packs? That will essentially kill Facebook. We ended up with some integration tests using SCAPI plus Linux TONTAP device. In the user space, we use SCAPI to craft certain packets, so you can actually craft any packet that you want with any signature. The Linux Transient TONTAP device is kind of a virtual device that you can expose this device to user space via file descriptor. At user space, we feed the crafted packet to this file descriptor. At the same time, we inject the compiled eBPF program to the XCP hook point. When we start writing to this file descriptor, the packet actually goes through the normal networking path from the type 0 device driver to XDP. And if we drop the packet, we will increment a counter in the user space. So we will tell whether we drop the correct packet from the value of the counter in the user space. So we also set up continuous integration for these test cases because we don't want to break our software when we introduce new features. This is very important to prevent regressions. So putting it all together, remember the droplet has to work with a shape, but one ugly thing about XDP is that it doesn't support program chaining, which means you can not call a function from a function. So we worked around this problem with two facilities. The first one is the BPF tail call, which essentially set jump. Once you call the BPF tail call, the control flow is passed to the next program. We also set up a persistent BPF map type program array, which is just an array of BPF programs, and you can use BPF tail call to jump between these programs. So the typical setup looks like this. So in the first place, we have a tool called XDP dump, which is used to dump packets, very similar to TTP dump. And then you have the droplet filters. Let's say the packet goes through XDP dump and then goes through droplet filter 1. If we decide this packet should be dropped, we just return an XDP drop. Otherwise, we will use BPF tail call to pass the control flow to the next filter in the chain. And eventually, after all the DDoS filters, the packet will reach our layer 4 load balancer code. And so we'll take care whether to send this packet to the other host or just pass it to the kernel. So let's shift the gear to talk about some operational lessons that we have learned in the last couple of years. So in the first place, it's very important for DDoS protection to have a regular red team exercise. So the idea here is to have an end-to-end testing of the entire pipeline for both detection and mitigation. So in the detection part, we want to see how fast we detect, and if there is any missing signal that we can use to help us detect faster. For the mitigation part, we want to see how quickly we come up with the attack signature and push the mitigation into production. We want to also see whether the production traffic is impacted, whether we cause any negative user experience. It's also important to see whether there are any opportunities to improve the tooling that can help us both fast detection and fast mitigation. So one additional aspect about operating DDoS mitigation is about monitoring. So we developed various kind of tools. The first one shown here is the standard BPF tool to show which program are running in the kernel. So in this case, it has a simple name called filter1. The time when this was loaded into the kernel and the size of the BPF program and which BPF maps the program refers to. We also developed our own droplet control tool. So here we're showing the 3 filters in the DDoS filter chain with different pipe and path index. The pipe here, which means which next DDoS filter should be called, and the path index here means which, let's say we decided this is a legitimate packet, which BPF program index we should call. And lastly, it has a default path. So here are one interesting story about the bug that we had in our production code. It's related to the hot reload, and it's very hard to get it right. So we used to reload the entire filter chain once the configuration for the filter changed. So the process here is obvious. You get a faster response time, but it's also quite easy to introduce regressions. So at one time, we had a bug that the tail call default, there was a missing filter because the source code cannot be compiled. And that led to egress drop because the default tail call behavior is to pass the pass the packet directly to the kernel instead of going through our layer 4 load balancer code. The solution here is to have like a multi-phase staging rollout. So you essentially go through the canary phase, the deploy phase, the activate phase, and you don't do this in one go. You start with 1% and with 5%, with 10%. We also preserve the big red button just for emergency uses. That means you can push the change to 100% of the edge network without going through the canary. So another bug we had with Droplet is about the timing of hook the code into the kernel and also the setup the map. So we used to hook the eBPF code into the kernel first and then set up the eBPF maps. But it creates a timing window that the BPF maps haven't been set up yet. Let's say if the map is actually a whitelist, then legitimate traffic will be blocked. If the map is a blacklist, then the bad traffic will go through. The solution here is to just hook the eBPF code into the kernel after the map setup, so you have the proper stats ready. Okay, so this is the last slide actually. So the next steps for Droplet were building a stateless firewall on top of Droplet plus eBPF. It's kind of in-house IP tables alternative. You can check out this upcoming Linux Plumber conference talk in Los Angeles. I think it's in September. There's also some outsider BP filter work that is aimed to replace IP tables as well. So we're also looking for a more tighter integration with our detection pipeline. So let's say we can use some machine learning technique to detect the anomaly patterns in the same packets. And we can come up with a signature in the PCAP expression and fit that into the mitigation pipeline. Yeah, so that's it.
Sit in front of the other Facebook servers that are processing the requests?
Yes. So our DDoS solution is integrated with the layer 4 load balancer code, but we also have layer 7 load balancer as well. So it's not like after layer 4 you go to backend service. There is the layer 7 between.
But no like specialized hardware?
No, we don't have any specialized hardware. It's entirely written in software for both DDoS and load balancer. Yeah.
Yeah. So how are the rules created? So I get a sense of how the rules are implemented or how the policy is implemented. Who comes up with the original rules that it's happening at?
So there are, in my opinion, there are two types of rules. The first one is the dynamic rules. Let's say you want to rate limit on a per flow basis or on per source IP basis. The other type of rule is the static rule, which we look at the previous attack signatures and we come up with PCAP signatures to match these previous attacks. Yep.
All right. Yeah.
So you mentioned you also have a layer 7 load balancer.
Yes.
Have you given a thought of whether that needs a DDoS solution too, or do you find that usually layer 4 is where the problems are?
I mean, the layer 4 is primarily driven by the brute force approach, which means the attacker sends a lot of packets to our services, right? I think the layer 7 is more like a web application firewall type of stuff, which is we're also currently building.
I have a question. So when you showed the chain of filters that had multiple BPF programs, I saw droplet twice. So does it like, multiple programs can choose to have different kinds of filters and drop packets, right? Is there a restriction on how many of those can be, or you can have infinite number? Or
I think the limit is 32.
I see.
So that's the inherent to the BPF system.
I see. Okay. Right.
So that's basically the size of the program. That's a number of BPF tail calls you can perform. So yeah, so essentially you can only jump 32 times.
So number of BPF programs can be at max 32. So yeah, I guess. Yeah. Any questions? All right, for you.
We have the state machine for each filter. So let's say whether the filter is compiled, whether it's attached into the kernel. That's one part. The other part is in the filter source code, we increment counters when we drop a packet or pass a packet. So we get an idea of how many packets have been processed, how many have been dropped.
Right. So just to add context to people, this probably is more of a BPF question, but this seems like you almost move some of the kernel programmability to user space, right? Now, what makes it safe to use? I could write any code that crashes a kernel probably with disastrous consequences, right?
That's why the BPF kernel verifier comes into play. Essentially, it verifies that your program doesn't do any crazy things. Okay. And if it does crazy thing, it will just bail out.
Yeah. Right. Cool.
Similar to static analysis.
Yeah. And bailout means it doesn't load the program, I suppose.
Correct.
Yeah, okay. So, all right. Cool. If there's a questions, like, do we wait for the next talk or we can start? All right. So the next talk is also about using another emerging technology for in IoT context. The speaker is Nicholas Alexopoulos. He's a doctoral researcher at Telecooperation Lab at Darmstadt University of Technology. He's interested in security, applied cryptography, computational trust. His latest interest, of course, is in designing secure, decentralized trust management systems. So this is how to use that infrastructure to secure trust in IoT networks. Right.
Hello, everybody. Thanks for being awake, most of you at least, this time. So this is different than the other papers in this workshop in that it is more of a position paper in order to start discussions on the topic than actually some implement system. Basically what we did is we approached in a systematic manner, like a scientific manner, the ongoing hype about blockchain and IoT. So let's start. This talk is about what the IoT can enable, understanding the security and privacy implications, and proposing a direction towards a solution, and discussing how these ideas can be realized through concrete mechanisms. So the agenda is as follows. First, we're going to talk about, give a little bit of a background on access control historically, very historically. Then talk about the IoT, the sharing economy, what can enable, and what are the new challenges in access control and trust management. Then proceed to a strawman solution, a design that expresses, let's say, the state of the art out there at the moment. Point out why we need more, and especially focus on the area of scalability for this talk, and proceed then to go over some challenges and open research problems in several areas of computer science. So a quick history on access control. It started with physical locks, let's say ancient access control, like this, not so ancient, but still old lock on the right. Then we got the permissions of, as implemented in the Unix kernel, which became standard for access control. And then we have more modern approaches like that on smartphones, and more recently in cyber-physical systems, which is actually our setting. And in this talk, when I talk about access control, I'm not referring to biometric authentication or this kind of access control, but more about remote access control, as we will see later. So the approaches that have been proposed for these issues from the start of this discipline have been traditional access control lists, role-based access control, or attribute-based access control, which are based on certificates like X509 certificates, and sometimes also PGP certificates. There's the Kerberos system, the ticketing system, and after that there was this general notion, like Matt Blaze proposed this generalized notion of managing trust, meaning that you need some information in order to make a decision on something, and it can be generalized outside of access control. After '96, there has not been such a dramatic progress in this area, I would say. So we have a lot of trust and reputation models that can support this whole trust management, decision supporting tool, and especially access control for cloud environments, which became the next big thing in our area. Why we need new stuff now? It is because the IoT and smart devices have enabled new economic models, new forms of interaction. And one of them is the sharing economy. So the sharing economy has to do with peer-to-peer sharing of physical and digital goods. And it's supposed to increase utilization of resources, help the environment through the effects of this. And a recent PricewaterhouseCoopers report places the projected value of the shared economy to $335 billion by 2025. However, when we talk about sharing economy today, most of its more strong supporters say it's not implemented as it should be. It's really centralized. A lot of companies make huge profits of relaxed relations between employees and employers. And we do not actually have sharing at the moment, because we don't have the core security infrastructure for this, which is distributed access control, trust management infrastructure. So to put things in context through a simple example about a smart car. So suppose Alice owns the said car, a four-door car, and is willing to share it. Bob is looking for a four-door car to take a trip in Budapest this weekend. Bob finds Alice and asks her if she will allow him to rent the car and offer some compensation. Alice decides that she trusts Bob and delegates some credentials to Bob that he can take out in front of the smart lock of the car, or the smart car, and then use it as said in the policy. So the central theme in this cooperation is trust, decision-making, and access. So going through the new challenges that the sharing economy brings in relation to older access control paradigms, we would want a solution that is decentralized, meaning no single point of failure in the decision-making procedure, but also distributed in terms of availability and processing. Apart from this, we also need richer policy expressions that also take into account context. For example, you can use a car only in Budapest, not outside, and time also. And as some of you may have noticed before, there are other decisions to be made. For example, if Alice will delegate the certain credential in order to allow this access, so we need some way to have a notion of trust, of experience and incentive-based trust. And I'm going to go into this in more detail later. We also want to have transparency of the trust information, especially when we also have negative credential, as we say, meaning some negative trust information that Bob may not want, to produce willingly to the smart lock in order to evaluate a policy. And of course, we have to go for thousands of, web pages to millions and even billions of devices. So scalability is a major issue here. And linking to this, we also have to take into account the not so good connectivity of IoT devices, especially when they're moving through different areas and their processing capabilities. Finally, we cannot have such a system without going over the privacy prerequisites for such a system that are not so clear upon first inspection, but we're going to go a little bit deeper into. So, a way to build a decentralized system is to use a distributed ledger. And what this means is just a text file that is maintained by a few nodes collectively. And the major breakthrough came in 2008 when Bitcoin, with a Nakamoto consensus, as it became known, the proof of work consensus algorithm, enabled what before was seen as impossible to have consensus and open system. Basically what it did is it used some proof from the physical world, from outside the system, meaning proof of possession and execution of computing power, and put this from the physical world into the digital world, into the system, in order to have leader election. And this was a big breakthrough. Bitcoin was used to maintain a cryptocurrency, meaning a text file that keeps track of the balance of each individual, each key, let's say. A few years later, Ethereum came over, which had a Turing-complete scripting language. So instead of putting in this text file only, let's say, the amount that is charged to an account, you can put any piece of code and execute this piece of code, and this can also change the state of this text file, ledger, as we call it. And in security terms, we can think of the distributed ledger as acting somewhat like a trusted third party, but with public internal state. So nothing is secret, there's full transparency, but correctness is guaranteed under the well-defined assumptions. So towards a decentralized sharing economy, the idea is to substitute these big service providers by open governance through a distributed ledger somehow, and this way allow real peer-to-peer exchange and sharing of assets. And actually some startups have caught up to this idea, like Slokit, for example. Slokit, if you don't know, their developers are the ones that also start the DAO. And so it's been kind of slow after the DAO thing, but we feel that research and systematic science has to catch up faster than we did with Bitcoin, for example. So a strawman solution would look something like this. We have Bob, who wants to have access to a smart lock, to the car, let's say, and he sends a transaction to the distributed ledger, let's say the Ethereum blockchain that's running out there. And Alice sees this transaction, decides she wants to do this, and issues a credential, which can be as simple as a digital signature on the public key of Bob and the lock, signaling that Bob has the access right to use this lock. And the lock would then access the distributed ledger and check for a credential that bears its public key. There are some fundamental problems with this design. First, there's no support for decision-making, whether or not to issue the credential. And in all digital systems, this support is crucial. Second, we don't even know why we use the blockchain here, like to put this credential that Alice could have given to Bob, and Bob could have just, showed to the device. So the use of a distributed ledger should only be made when consensus guarantees lead us to security proofs about properties. Third, the low-powered IoT devices do not have the capacity to maintain blockchain nodes or even run thin clients. So there need to be an infrastructure for very thin clients that don't even need the header information in order to verify transactions. So regarding the first challenge, that of helping decision-making, digitizing trust, as we say, there have been a lot of reputation systems like the eBay system or even more advanced systems. And there has also been work in the field of computational trust, as it is said, which is a generalization of reputation systems, meaning that trust is portrayed as a Bayesian probability, for example, in certain trust. And generally, all these systems, the reputation systems, have one thing in common. They have one basic assumption that each player is like 60, 70, 80, but some X% good. For example, if he makes 8 out of 10 transactions good, then it means he's 80% good, and for the next 10 transactions, he's going to make 8 of them, like he'll be honest in 8 of them, which is quite a strong assumption. There's another approach, more recent, for using financial risk and collateral as a pointer of trust. So for example, there was a paper at FC last year that uses lines of credit in order to prove game theoretically that if a line of credit, let's say for 50 euros exists between two individuals that do not know each other, then a transaction up to 50 euros will be proven to be correct, like the seller will send the product, because otherwise, game theoretically in their model, there would be another play that would maximize the profit of the adversary. So here, the basic question is, how can we express trust in a way that is closer to what we have in the real world when making a transaction? Because it's not only reputation, it's our minds do not work as a rational player all the time. So this is a challenge, how to capture the real world trust in a system. Now, for the scalability, we are looking at the problem in a three-layer architecture. We have a global layer that can be a global distributed ledger, like Ethereum. We have a first layer, like a shard layer. I will go into it later in more detail. And a local layer, which are the embedded devices behind an internet access point. Sharding has been a major driving force for the last couple of years more about scaling out blockchains. And there have been some papers very recently, but the problem is very, very difficult, and it's still not solved. But what we want is not just to solve the sharding problem for distributed ledgers in general, but we want an application-specific sharding that will increase the scalability of our system. So going to the layers, level 0 is a local layer with the embedded devices. Level 1 will be the shards layer, which could be thought of as smart city shards that manage the devices that fall within the premises of a city or a namespace, let's say. And the third is a global layer that manages everything. Going into more detail about the level 0, the embedded devices, this is where devices live in this level, and they can also move between different access points. They're not bound to an access point, but they depend on it to get network connection to the upper layers. So devices read their policies and the credentials from the upper layers. There is a need for very light clients, but still with reasonable security guarantees in order to cope with the reduced resources. In addition, devices need to sense context and put this into their policy expressions, and the credentials need to be expressed in a hybrid way, meaning a mix of on and off-chain credentials depending on the reason or the necessity of using a distributed ledger for the given credential. If there is a danger that a double spending equivalent attack is going to take place or not. The level 1 has to do with the shards. So shards can be seen as different namespaces, and each device or user, each entity, belongs to only one namespace. As we will see, this relation is maintained by the global distributed ledger. They can be imagined as being city scale, but this is just logical boundary in the namespace. And they can be maintained by a permissioned ledger, a central authority, or generally with not bound how they will be maintained, but each entity can decide whether or not they trust the information maintained in a given namespace. So each entity has the opportunity to say, oh, I trust this provider or this namespace or this permissioned ledger maintained by these people, for example, these nodes, or not. And finally, the global governance and the relation between entities and namespaces is maintained by the upper layer, the global distributed ledger. And also, all financial transactions are resolved here. So, going through other open challenges, after giving some directions towards solutions. So, as we talked before, shards can be made out of committees of, again, permissioned blockchains, as we say, running a permissioned consensus algorithm like traditional Byzantine fault-tolerant algorithm. And this is also what general blockchain sharding proposals look into. And the question is how to form the committees in a way that they are more likely to be honest if we consider there is a presence of adversaries in the whole system. Second, there is a big challenge of designing very light clients. So there are light clients where the devices need to download the headers of the blockchains, but maybe they cannot even do so, and they need to emulate a trusted party that they can ask and get a response. And we think that promising solutions towards this are economically motivated models that if some entity gives a bad reply, they will be penalized. And this reply can be automatically verified that it's bad through a smart contract. Third, there is a need for a new policy language that will balance between expressiveness and expressing all this new information that we can get from IoT devices, sensors, context, and other modalities, and that can also be understandable by humans. Another challenge is that of digitizing trust. So having a trust management system that will enable Alice to make the decision whether Bob is trustworthy in order to give him the credential to access the resource. And finally, privacy is also very important. We have some solutions, namely what is called anonymous credentials, that can lead us to some good privacy guarantees. But then again, there are also other problems that are not so technical, and maybe they are the most important for these issues. For example, the business model, incentives for the participants, and also relating to privacy, law. So for example, there has been a lot of discussion lately about criminalizing encryption and privacy, and this is also very interesting to see how it goes. So on this positive note, I will conclude with saying that we believe a decentralized infrastructure is vital for a true sharing economy. And there is a need for new approaches in several areas, but the distributed ledgers in general offer the way, and they can enable decentralized governance, which is very important. And as I said before, there are many challenges in many areas of computer science, ranging from cryptography, distributed systems to network systems. So thank you very much, and I'm here to answer any questions.
There's a collection of papers from 2011 to 2014 that talk about, for instance, distributed authorization knowledge language that talk about many of these issues. Are you familiar with that?
I think that there are even a lot of papers from earlier about different languages for authorization and policy expression, like different variations of data log and distributed logic expressions.
Yeah, some of that. Yeah, but,
like SecPal, for example, that is pretty recent. Like it's a Microsoft thing.
Why does that not?
Yeah, so as a construct, like what we can say, we even had the tools from earlier. I would say from like Policymaker, like 96 had this language that we could use. First order logic existed like for a long time. But the important thing is to see exactly what things are important, how we can capture context, which context details are important for this, to have more understandable and precise. So we have the tools, yes, we have data log, we have the tools how to do it, but we just need to have a more specific language that is also easier for humans to understand.
Specifically, DeepCal talks about many of the issues that come when we have federated authorization, and then it's not very trivial to mix.
No, it's not trivial at all. Okay, so So we want to put on the blockchain only things that are subject to manipulation, let's say. So for example, the one thing that is going to be maintained in the blockchain for sure is the experience or incentive-based trust evidence about Bob and Alice, meaning it could be financial chains of credit in order to have a game theoretic incentive to participate, to be honest, or it could be experience derived trust evidence. Where are the slides?
You just went past them.
Okay. No, there. Okay, sorry. Okay, sorry. So first, Bob would request access. Alice could have already put the access policy written in Datalog or some logic on the blockchain, so the device could have access through a very light client to this policy. And then Alice could grant the credential to Bob, and this could be both on and off the blockchain, either on or off the blockchain, depending on what this credential means. For example, if Bob wants to have exclusive access, so nobody else, so he's guaranteed that nobody else will have access at this data point, then Alice would need to store the credential on the ledger in order to avoid this double spending equivalent attack, that somebody else will also have access in the same time frame. And of course, in all of this, we assume that the device is trusted by both parties, which is another topic, can be, so it's a big topic, like trusted hardware, how this can be implemented. But we assume the device is honest, it reads the policy, the credentials presented by Bob or also stored on the ledger, and makes the decision by evaluating the policy, and then outputs yes or no answer to Bob. I wouldn't do this manually, of course, so this would be done automatically. I mean, the sharing economy is just one use case of distributed trust management systems that have been around for a lot of years. But especially in the IoT, it is one use case that can have a lot of economic impact.
I think you two need to talk more to actually figure out that. So we have time probably for one more question. Go ahead.
I am recorded. So yeah, they do some stuff similar.
All right, cool.
Are you with them? They are doing some things, but they have not looked into this area specifically, and we can talk offline about them.
All right, thank you. That's a very exciting talk.
Thanks.
So, right. Theo will make some closing remarks.
All right, on behalf of myself and my co-chair who's not here, Shrikant, I want to thank everyone for being here and still being awake, even though it's been a very long day with the jet lag. So this was a very successful workshop. We had a lot of exciting talks and very good conference engagement, even until the very, very end. We were still being very contentious and discussing, which is kind of the whole point of this, is to get papers where people will have discussion, get people to think either they agree or they disagree, but still have some discussion. So I think this was very good and successful. Now we're basically at the end of the workshop. The main thing I wanted to say is there's actually a reception later tonight at 8 o'clock. It's going to be downstairs. Oh, it's going to be on this floor. So go out, enjoy the Budapest National Day. Okay, so it's from 9 to 9:30. So go out, walk around, come back at 8 o'clock for the reception, then go back outside for the fireworks. All right. Bye.